The death of a star is a spectacular event, each one leaving behind an eternal mark on the cosmos. Stars are not immortal, their lives are dictated by the finite supply of nuclear fuel in their cores. When that fuel runs out, gravity takes over, and the star collapses. What happens next depends on the star's mass, a destiny preordained from the moment it was born. For small to medium-sized stars like our Sun, the process begins when hydrogen fuel in the core is depleted. Fusion slows and gravity causes the core to contract while the outer layers expand, turning the star into a red giant. In this swollen state, the star engulfs nearby planets, its outer layers puffing away into space. What remains is a planetary nebula, a shell of glowing gas surrounding a hot, dense core. This core, known as a white dwarf, is no larger than Earth but has a mass comparable to the Sun. Over billions of years, it will cool and fade, becoming a dark, inert black dwarf. For larger stars, however, the end is cataclysmic. When their cores run out of hydrogen, heavier elements like helium, carbon, and oxygen begin to fuse. This process creates layers within the star, like an onion, with iron accumulating at its core. Iron is the end of the line for fusion. It cannot release energy through fusion like lighter elements. As the core fills with iron, the outward pressure of fusion ceases, and gravity causes the star to collapse in an instant. The collapse triggers a supernova, an explosion of unimaginable power. In a fraction of a second, the core compresses into an object so dense that a teaspoon of its material would weigh billions of tons. The shock wave from the collapse blasts the outer layers into space, enriching the universe with heavy elements like gold, silver, and uranium. These elements will one day become part of new stars, planets, and even life itself. Supernovae are the universe's way of recycling, taking the remnants of dying stars and using them to create new worlds. What remains after a supernova depends on the star's original mass. If the core is between 1.4 and 3 times the mass of the Sun, it forms a neutron star. These are some of the densest objects in the universe, consisting almost entirely of neutrons. A neutron star is only about 20 kilometers across but contains more mass than the Sun. Their magnetic fields are incredibly strong, and some neutron stars emit beams of radiation as they spin, appearing as pulsars when observed from Earth. If the core is more than 3 times the Sun's mass, the result is a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. Black holes are the ultimate endpoints of stellar evolution, and they continue to fascinate scientists and the public alike. Some black holes, known as stellar mass black holes, are the remnants of massive stars. Others, called supermassive black holes, reside at the centers of galaxies and have masses millions or even billions of times that of the Sun. How these supermassive black holes form is still a mystery, but they play a critical role in the formation and evolution of galaxies. Even the material ejected during a star's death contributes to the cosmic cycle. Supernova remnants, like the famous Crab Nebula, are vast clouds of gas and dust that spread out over thousands of years. These remnants become part of interstellar space, where they eventually cool and collapse, forming new stars and planetary systems. In this way, the death of one star sets the stage for the birth of others, continuing the cycle of creation and destruction that has shaped the universe since its beginning. The most mind-boggling aspect of this process is its connection to us. Every atom in your body, every molecule in the air you breathe, was forged in the heart of a star that lived and died billions of years ago. The iron in your blood, the calcium in your bones, and the oxygen you inhale were all created in stellar furnaces and scattered across the universe by supernovae. When we look up at the night sky, we're not just seeing stars, we're seeing the very factories of life. But stars are not isolated entities. Their births, lives, and deaths are deeply intertwined with the galaxies they inhabit. Galaxies are not just homes for stars, they are dynamic, living systems that evolve over billions of years. The interplay between stars and galaxies is one of the most fascinating and complex aspects of astrophysics. Shall we venture into the mysteries of galaxies next? Galaxies, the cities of the universe. Galaxies are the grand metropolises of the cosmos, vast collections of stars, gas, dust, and dark matter bound together by gravity. They come in many shapes and sizes, each telling a unique story of cosmic evolution. From the elegant spirals of the Milky Way to the chaotic irregulars and the ancient ellipticals, galaxies are the building blocks of the universe on the largest scales. Our galaxy, the Milky Way, is a barred spiral spanning over 100,000 light-years. It contains around 100 billion stars, each with its own system of planets, moons, and debris. At its center lies Sagittarius A, a supermassive black hole with a mass equivalent to 4 million suns. This gravitational behemoth anchors the galaxy, influencing the orbits of nearby stars and shaping the movement of gas and dust. But the Milky Way is just one of countless galaxies in the universe. The Andromeda Galaxy, our nearest spiral neighbor, is slightly larger and on a collision course with us. In about 4.5 billion years, the Milky Way and Andromeda will merge in a spectacular galactic dance, forming a new, larger galaxy. These collisions are not as violent as they sound. The vast distances between stars mean that direct impacts are rare. Instead, the gravitational forces reshape the galaxies, triggering bursts of star formation and creating stunning tidal sails of stars and gas. Galaxies rarely exist in isolation. Most are part of clusters, groups of galaxies bound together by gravity. Our Milky Way belongs to the local group, which contains about 54 galaxies, including Andromeda and smaller companions like the Magellanic Clouds. Larger clusters, like the Virgo cluster, contain thousands of galaxies. These clusters themselves are part of even larger structures called superclusters, which form a vast cosmic web. The cosmic web is the universe's large-scale structure, a network of filaments made of galaxies and dark matter that stretch across billions of light-years. Between these filaments lie enormous voids, regions of space with very few galaxies. This web-like structure formed as gravity pulled matter together after the Big Bang, shaping the distribution of galaxies we see today. Dark matter plays a crucial role in galaxy formation and structure. Though invisible and undetectable directly, dark matter exerts gravity, holding galaxies together and influencing their rotation. Without dark matter, galaxies would fly apart, as their visible mass alone isn't enough to account for their observed behavior. Scientists estimate that about 85% of the matter in the universe is dark matter, making it one of the greatest mysteries in astrophysics. The life cycle of galaxies is a testament to the universe's dynamism. Young galaxies, rich in gas and dust, are fertile grounds for star formation. Over time, as their gas supply dwindles, star formation slows and galaxies age. Some become elliptical galaxies, dominated by older, redder stars. Others, especially those in clusters, may be stripped of their gas through interactions with other galaxies or the intracluster medium. These interactions can result in dead galaxies, no longer able to form new stars. Despite their differences, all galaxies share one thing in common: they are nurseries of life. The elements forged in stars, scattered through supernovae, eventually coalesce into planets and perhaps living organisms. Every galaxy, no matter its size or shape, carries the potential for worlds like ours, orbiting stars in the vast expanse of space. But galaxies are not static. They move, collide, and evolve, creating new phenomena and mysteries. How do supermassive black holes grow to such immense sizes? What role does dark energy play in the expansion of the universe and the fate of galaxies? These questions drive the frontier of astrophysics, pushing our understanding of the cosmos to new heights. Let's zoom in now and explore one of the most fascinating aspects of galaxies, their enigmatic centers. What lies within these galactic cores, and how do they influence the universe around them? The enigmatic cores of galaxies, supermassive black holes. At the heart of nearly every large galaxy lies a supermassive black hole, an object so dense that its gravity can warp space and time itself. These black holes, ranging from millions to billions of times the mass of the Sun, are among the most mysterious and powerful forces in the universe. But how did they form? And what role do they play in the evolution of galaxies? Supermassive black holes are thought to grow through a combination of accretion and mergers. In the chaotic early universe, dense regions of gas collapsed to form the seeds of these cosmic giants. As galaxies formed around them, these black holes fed on surrounding material gas, dust, and even stars, pulling it into a swirling disk called an accretion disk. As matter spirals inward, it heats up to extreme temperatures, emitting intense radiation. This process makes the regions around supermassive black holes some of the brightest in the universe, forming what we know as quasars. Quasars are active galactic nuclei, AGN, powered by supermassive black holes consuming vast amounts of material. They can outshine entire galaxies, visible across billions of light years. Observing quasars allows scientists to study the universe as it was billions of years ago, offering clues about the formation and growth of galaxies in the early cosmos. Some of the brightest quasars are powered by black holes weighing billions of solar masses, suggesting rapid growth in a relatively short cosmic time span. Not all supermassive black holes are active. In galaxies like the Milky Way, the central black hole, Sagittarius A, is relatively quiet, feeding on minimal material. Occasionally it flares as it consumes nearby gas or a passing star, but for the most part it lies dormant. However, even dormant black holes exert tremendous influence. Their gravity shapes the orbits of stars and affects the dynamics of the galactic core. Supermassive black holes also play a key role in regulating star formation within galaxies. When they are actively feeding, they emit powerful jets and winds that can heat or expel gas from the galaxy. This process, known as feedback, prevents gas from cooling and condensing into new stars. In this way, black holes act as cosmic thermostats, controlling the rate of star formation and shaping the evolution of galaxies. One of the most intriguing discoveries in recent years is the relationship between the mass of a galaxy's supermassive black hole and the properties of the galaxy itself, such as the mass of its central bulge. This connection, known as the black hole bulge relation, suggests a deep link between the growth of black holes and the formation of galaxies. How this relationship develops remains an open question, but it highlights the interconnectedness of all cosmic structures. The influence of supermassive black holes extends far beyond their host galaxies. The jets they produce, which can stretch thousands of light years, inject energy into the surrounding intergalactic medium. These jets can trigger star formation in neighboring regions or halt it, depending on the conditions. They also spread heavy elements forged in stars, enriching the universe with the building blocks of planets and life. Despite decades of research, supermassive black holes continue to challenge our understanding. How did they grow so quickly in the early universe? Do they harbor exotic states of matter at their cores? Could they serve as gateways to other regions of spacetime, as some theories suggest? Observatories like the Event Horizon Telescope, which captured the first image of a black hole's shadow, and next-generation telescopes like the James Webb Space Telescope aim to unravel these mysteries. But black holes are just one piece of the puzzle. To understand the universe as a whole, we must also explore the forces shaping its expansion and ultimate fate. Shall we journey next into the realm of dark energy and the accelerating universe? The accelerating universe and the mystery of dark energy. The universe is not static, it's expanding. This revelation, first uncovered by Edwin Hubble in the 1920s, transformed our understanding of the cosmos. Hubble discovered that galaxies are moving away from us, with more distant ones receding faster, a phenomenon explained by the expansion of space itself. But the story doesn't end there. In the late 1990s, astronomers made a groundbreaking and puzzling discovery: the expansion of the universe is accelerating. This acceleration defied expectations. For decades, scientists assumed that gravity, the attractive force pulling matter together, would slow the expansion over time. Instead, observations of distant supernovae revealed that something mysterious dubbed dark energy is driving the universe apart at an ever-increasing rate. Dark energy is now believed to make up about 68% of the universe, dwarfing the contributions of normal matter, about 5%, and dark matter, 27%. So, what is dark energy? The truth is, we don't know. It might be a property of space itself, as suggested by Einstein's cosmological constant, a term he originally introduced to stabilize his equations of general relativity. When quantum physics enters the equation, the vacuum of space isn't truly empty, it's filled with virtual particles that pop in and out of existence, generating energy. If this energy is constant across the universe, it could explain the accelerated expansion. Another possibility is that dark energy is a new and unknown force of nature. In this scenario, it might vary over time and space, influencing the expansion of the universe in ways we're only beginning to imagine. This idea ties into theories like quintessence, which propose that dark energy is dynamic rather than static. The effects of dark energy are profound. As space stretches, galaxies are carried farther apart, creating vast, ever-growing distances. Over billions of years, this accelerated expansion will reshape the universe. Eventually, galaxies outside our local group will become unreachable, moving so far away that their light will never reach us. The observable universe will shrink, leaving only the Milky Way and its closest neighbors visible, a lonely future for cosmic explorers. But dark energy doesn't just shape the distant future. It offers clues about the universe's ultimate fate. If its influence continues to grow, it could lead to a scenario known as the Big Rip. In this dramatic end, dark energy would overcome not just gravity but all the forces binding matter together. Galaxies, stars, planets, and even atoms would be torn apart, reducing the universe to a featureless expanse. Alternatively, if dark energy weakens over time, the expansion could slow and reverse, culminating in a big crunch where the universe collapses back into a singularity. Current evidence suggests a more moderate outcome, a universe that expands forever, but at an ever-increasing pace. This heat-death scenario would see galaxies drift apart, stars burn out, and matter decay into subatomic particles. In this future, the universe becomes a cold, dark void, with entropy reaching its maximum. Yet even in such a bleak vision, the universe's story doesn't truly end. Quantum fluctuations or unknown physics could spark a new cycle of creation, giving rise to a new cosmos. The discovery of dark energy has spurred countless questions and few answers. How does it interact with dark matter, the mysterious substance holding galaxies together? Could experiments on Earth ever replicate its effects? And what does it mean for our understanding of the fundamental forces of nature? These questions drive the work of cosmologists and physicists, whose insights may one day reveal the true nature of this enigmatic force. As we grapple with dark energy's mysteries, we're also uncovering deeper truths about the universe's infancy. Next, let's journey back to the first seconds of existence, where quantum mechanics and relativity collide, and explore how the seeds of today's cosmic structures were sown. Shall we delve into the quantum realm and the birth of the universe? 4-0. You said. The quantum birth of the universe. To understand the universe's earliest moments, we must journey back to the beginning literally. The Big Bang theory describes how the universe expanded from an extremely hot, dense state roughly 13.8 billion years ago. But the first fractions of a second after the Big Bang are where the most profound mysteries lie, a realm where quantum mechanics and general relativity intersect in ways that defy conventional understanding. In the first 104,310,43,1043 seconds, a period known as the Planck epoch, the universe was so dense that the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. This unification is beyond the reach of current physics, as we lack a complete theory of quantum gravity to describe it. However, physicists hypothesize that fluctuations in this unified field created tiny variations in energy density, the seeds of the structures we see today. As the universe expanded and cooled, it transitioned into the grand unification epoch. During this time, gravity separated from the other forces, leaving the strong nuclear force and electroweak force combined. This phase, lasting just 103,610,36,1036 seconds, gave rise to one of the most important events in cosmic history, inflation. Inflation was a period of exponential expansion, where the universe grew from smaller than a proton to the size of a grapefruit in a fraction of a second. This incredible burst of growth smoothed out irregularities and ensured the universe's large-scale uniformity. However, inflation wasn't perfectly smooth. Quantum fluctuations during this period were stretched to macroscopic scales, creating regions of slightly higher or lower density. These fluctuations would later become the galaxies, stars, and planets of today. When inflation ended, the universe entered the electroweak epoch, around 101,210,12 seconds after the Big Bang. Here, the strong force separated from the electroweak force, and the universe was dominated by a hot, dense plasma of particles and antiparticles. This plasma was in a constant state of annihilation and creation, a chaotic dance of matter and energy. As temperatures dropped, the Higgs field emerged, giving mass to certain particles through the Higgs mechanism. This event laid the foundation for the diversity of particles that make up the universe. Next came the quark epoch, where the universe was filled with a soup of quarks, gluons, and leptons. These quarks, the fundamental building blocks of matter, were unable to combine into protons and neutrons due to the extreme heat and density. But as the universe continued to expand and cool, it entered the Hadron epoch around 10 to 610 seconds after the Big Bang. Quarks began to bind together, forming protons and neutrons, the building blocks of atomic nuclei. By the time the universe was a few minutes old, it had cooled enough for these protons and neutrons to undergo nuclear fusion, forming the first atomic nuclei in a process called Big Bang nucleosynthesis. This created the lightest elements, hydrogen, helium, and trace amounts of lithium. These elements would later become the raw materials for stars and galaxies. However, the universe was still far from transparent. For the next 380,000 years, it remained a hot, dense plasma where photons were trapped, unable to travel freely. This era, known as the photon epoch, ended when the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This event, called recombination, allowed light to travel freely for the first time. The photons released during this period still exist today as the cosmic microwave background, CMB, a faint glow that permeates the universe and serves as a snapshot of its infancy. The quantum birth of the universe not only set the stage for cosmic evolution, but also left behind enduring mysteries. What drove inflation, and why did it end? What is the true nature of the quantum fluctuations that shape the universe's structure? And could the Big Bang itself have been part of a larger cycle, a cosmic rebirth from the remnants of a previous universe? As we ponder these questions, let's move forward in time to explore how these early events gave rise to the cosmic web, the vast and intricate structure that defines the universe today. Shall we? The cosmic web. The universe's grand structure. As the universe evolved from its hot, dense beginnings, it gradually organized itself into an intricate tapestry known as the cosmic web. This grand structure stretches across billions of light years, composed of filaments of galaxies and dark matter, vast voids and massive clusters. To understand how this stunning architecture formed, we must follow the story of the universe's matter from its earliest moments. After recombination, when the universe became transparent to light, the first atoms formed a mostly uniform sea of hydrogen and helium gas. However, the quantum fluctuations left over from inflation ensured this uniformity wasn't perfect. Tiny variations in density, imperceptible at first, began to grow under the influence of gravity. Over hundreds of millions of years, these denser regions pulled in more gas and dark matter, forming the seeds of galaxies, clusters, and superclusters. The dark matter was crucial in this process. Though it doesn't emit or absorb light, dark matter's gravitational pull provided the scaffolding for cosmic structure. As normal matter fell into the gravitational wells created by dark matter, it clumped together and began to form the first stars and galaxies. Without dark matter, the process would have taken far longer, and the universe might look very different today. These structures didn't form in isolation. Over time, gravity pulled galaxies and clusters together, creating the filamentary structures we see today. These filaments are surrounded by vast voids, regions of space, almost entirely devoid of galaxies. These voids can span hundreds of millions of light years, making them some of the largest features in the universe. One of the most striking aspects of the cosmic web is its fractal-like pattern. On smaller scales, galaxies group into clusters and superclusters, like the Virgo cluster or the immense Laniakea supercluster, of which our Milky Way is a part. On larger scales, these clusters are connected by filaments of galaxies, forming a network that resembles a three-dimensional spider's web. At the intersections of these filaments lie the universe's most massive structures, galaxy clusters. These clusters, containing thousands of galaxies, are held together by the immense gravitational pull of dark matter. They are also home to hot, X-ray emitting gas, which outmasses the galaxies themselves. The largest clusters, such as the Coma cluster, are cosmic giants that have been billions of years in the making. Yet, even these massive clusters are mere nodes in the cosmic web. The spaces between them are filled with the intergalactic medium, igneous, a tenuous gas that spans the universe. This gas, enriched with elements from ancient supernovae, plays a critical role in galaxy formation and evolution. It is also a crucial tracer of dark matter, as the gas tends to follow the gravitational pull of dark matter filaments. The cosmic web didn't just shape galaxies, it also influenced the distribution of the elements. As galaxies formed and evolved, they enriched their surroundings with heavier elements forged in stars. These elements spread through supernova explosions and galactic winds, seeding the intergalactic medium with the ingredients for future star and planet formation. The discovery and mapping of the cosmic web are among modern astronomy's greatest achievements. Surveys like the Sloan Digital Sky Survey, SES, and the Dark Energy Survey have provided detailed maps of the large-scale structure of the universe, confirming the predictions of cosmological models. These surveys reveal not just the visible distribution of galaxies, but also the underlying dark matter framework, inferred from the motions of galaxies and gravitational lensing. But the cosmic web is far from static. Over billions of years, gravity continues to pull matter together, while dark energy drives the universe's expansion, stretching the web and deepening the voids. This interplay between dark energy and gravity will determine the ultimate fate of the cosmic web. Will the filaments stretch and fragment as the universe accelerates into a cold, dark future? Or will new physics emerge, altering the course of cosmic evolution? The cosmic web is a testament to the universe's complexity and beauty, a structure that connects the smallest quantum fluctuations to the largest cosmic features. But to fully appreciate its significance, we must also explore the galaxies it houses, their formation, evolution, and the unique phenomena they host. Let's zoom in now to examine the life cycles of galaxies and their role as cosmic nurseries for stars and planets. Shall we continue? The life cycles of galaxies, cosmic nurseries and giants of evolution. Galaxies, the luminous hubs of the cosmic web, are the crucibles where stars, planets, and perhaps life itself are born. They are dynamic systems that evolve over billions of years, shaped by complex interactions between gravity, gas, dark matter, and even their neighboring galaxies. To understand the life cycles of galaxies is to unravel the story of cosmic evolution itself. Galaxies are born from the collapse of massive clouds of gas and dark matter. In the early universe, as dark matter clumped together into halos, it pulled in vast amounts of hydrogen and helium gas. This gas, cooling under gravity, ignited the first bursts of star formation, marking the birth of protogalaxies. These primitive galaxies were small and irregular, chaotic in structure compared to the majestic spirals and ellipticals we see today. As time went on, these protogalaxies collided and merged, giving rise to larger and more organized systems. Mergers played a pivotal role in shaping galaxies, often triggering intense bursts of star formation as gas clouds were compressed during the collisions. These starbursts could create hundreds of stars per year, rapidly depleting the galaxy's gas reserves. The remnants of these collisions are evident in the massive ellipticals that dominate galaxy clusters today. Galaxies come in many forms: spirals, ellipticals, and irregulars, each representing a different stage of evolution. Spiral galaxies, like our Milky Way, are rich in gas and dust, with active star formation in their arms. Their flat, disk-like structure rotates around a dense central bulge, where older stars and sometimes a supermassive black hole reside. Spiral galaxies are the most photogenic, their elegant shapes illuminated by young, blue stars. Elliptical galaxies, on the other hand, are massive, featureless systems with little gas or dust. They are composed mostly of older, redder stars, a sign that star formation ceased long ago. These galaxies are often the result of multiple mergers, their chaotic histories erasing the structured beauty of spirals. Despite their age, ellipticals are home to some of the universe's most extreme phenomena, such as densely packed star clusters and massive black holes. Irregular galaxies, as their name suggests, lack a defined shape. They are often smaller and more chaotic, their irregularity caused by gravitational interactions or mergers with other galaxies. These galaxies are more common in the early universe, when collisions were frequent and galaxies were still forming their structures. At the heart of every galaxy is the interplay between gas, stars, and dark matter. Gas is the lifeblood of galaxies, the raw material for star formation. In spirals, gas flows along the arms, collecting in dense regions where it cools and collapses into new stars. In ellipticals, however, most of the gas has been consumed or expelled, leaving a population of aging stars with little hope for renewal. But galaxies don't evolve in isolation. They interact with their environment, exchanging gas and energy with the intergalactic medium. Galactic winds, driven by supernovae or active black holes, can blow gas out of a galaxy, slowing or halting star formation. These winds enrich the intergalactic medium with heavy elements, spreading the building blocks of planets and life across the cosmos. In galaxy clusters, interactions are even more intense. Galaxies can collide, merge, or strip gas from one another through a process known as ramp pressure stripping. These interactions are visible in phenomena like tidal tail streams of stars and gas torn from galaxies during close encounters. Some galaxies, known as starbursts, experience brief but intense periods of star formation triggered by these interactions, while others are left as dead systems, unable to form new stars. Yet, even in death, galaxies continue to shape the universe. Their remnants, whether as ellipticals, globular clusters, or even black holes, contribute to the cosmic tapestry. Over billions of years, these remnants will merge into larger structures, forming the next generation of galaxies. The cycle of galactic evolution is endless, a testament to the universe's creativity and resilience. From the fiery birth of protogalaxies to the serene stillness of ancient ellipticals, galaxies encapsulate the entire history of the universe. They are not just clusters of stars and gas, but the engines of cosmic change, driving the formation of stars, planets, and perhaps life. Let's now dive deeper into one of the most fascinating aspects of galaxies: their role as cradles of planetary systems and the potential homes of life. Shall we? Galaxies as cradles of planetary systems and life. Galaxies are not merely collections of stars, they are cosmic nurseries where planets form and life might arise. Within their sprawling reaches, stars and planets emerge from clouds of gas and dust, and the elements forged in earlier generations of stars provide the raw materials for the diversity of worlds we see today. The story begins in the dense molecular clouds scattered throughout galaxies, particularly in spiral arms rich in gas and dust. These regions, often called stellar nurseries, are where gravity pulls material together to form new stars. Around these young stars, leftover gas and dust coalesce into protoplanetary disks, swirling structures that eventually give birth to planets. The interplay of gravity, temperature, and motion in these disks determines whether they form rocky planets, gas giants, or icy worlds. Our own solar system was born in such a process, within the Milky Way's Orion Arm. About 4.6 billion years ago, a massive molecular cloud collapsed to form the Sun and a swirling disk of material. Over tens of millions of years, particles in this disk collided and stuck together, growing into the planets, moons, and asteroids we know today. The Earth, uniquely positioned in the Sun's habitable zone, became a cradle for life, thanks to the availability of liquid water and a protective atmosphere. But the Milky Way is far from unique in its ability to host planetary systems. Recent discoveries have revealed that planets are ubiquitous throughout the universe. Using tools like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, astronomers have identified thousands of exoplanets orbiting stars in distant galaxies. These planets range from Earth-like worlds in habitable zones to hot Jupiters orbiting perilously close to their stars. What's more astonishing is the sheer diversity of planetary systems. Some stars host tightly packed systems of rocky planets, while others boast enormous gas giants orbiting at vast distances. Many planets exist in configurations that defy our expectations, such as rogue planets drifting through space without a host star, likely ejected from their systems during chaotic gravitational interactions. The ingredients for life, water, organic molecules, and energy sources are also surprisingly common. Complex organic compounds have been detected in protoplanetary disks, comets, and even the interstellar medium. Water, in liquid, ice, or vapor form, has been found throughout the solar system, from Europa's subsurface oceans to the geysers of Enceladus. If these conditions are replicated on exoplanets, the potential for life beyond Earth becomes tantalizingly real. Galaxies themselves play a crucial role in determining where life might thrive. Their structure, composition, and environment influence the types of stars and planets they produce. For example, spiral galaxies like the Milky Way, with their rich gas supplies, are fertile grounds for star and planet formation. In contrast, elliptical galaxies, which are largely devoid of gas, are less likely to host young planetary systems. The location within a galaxy also matters. The concept of the galactic habitable zone suggests that not all regions of a galaxy are equally suited for life. In the Milky Way, this zone lies between the crowded, radiation-filled galactic core and the sparsely populated outer edges. Here, stars are spaced far enough apart to avoid frequent supernovae, yet close enough to recycle heavy elements for planet formation. The interplay between stars, planets, and their galactic environment underscores the interconnectedness of cosmic systems. Supernovae enrich galaxies with the heavy elements needed for rocky planets, while the energy from active galactic nuclei can influence star formation. Even interactions between galaxies can spread the ingredients for life, as gas and dust are exchanged during collisions and mergers. Despite the growing catalog of exoplanets and the increasing understanding of galactic environments, the ultimate question remains: are we alone? The search for extraterrestrial life, whether microbial life on Mars or advanced civilizations orbiting distant stars, is one of the greatest endeavors in science. Instruments like the James Webb Space Telescope and upcoming missions like the Extremely Large Telescope, ELT, may soon provide answers by analyzing the atmospheres of exoplanets for biosignatures. As we ponder these possibilities, let's shift our gaze back to the larger picture. How do these planetary systems, scattered across billions of galaxies, contribute to the universe's grand narrative? And what does their presence tell us about the future of cosmic evolution? Shall we explore the ultimate destiny of stars, planets, and galaxies in the ever-expanding universe? The ultimate destiny of stars, planets, and galaxies. The universe, though dynamic and vibrant today, is not eternal in its current state. Every star, planet, and galaxy will eventually meet its end, their fates tied to the inexorable flow of cosmic time and the laws of physics that govern everything. To understand the ultimate destiny of the cosmos, we must follow the long-term evolution of its fundamental components. Stars, the brilliant engines of the universe, are finite in their lifespans. As their nuclear fuel runs out, they will fade and die. For stars like the Sun, this process will take billions of years, culminating in the gentle shedding of outer layers and the formation of white dwarfs. These remnants will slowly cool over trillions of years, becoming cold, dark black dwarfs, silent monuments to the universe's once bright past. Larger stars will meet a more violent end, exploding as supernovae and leaving behind neutron stars or black holes. These remnants, though no longer producing energy, will persist for eons, shaping their surroundings with intense gravitational influence. Over quadrillions of years, the black holes themselves may gradually evaporate through Hawking radiation, disappearing into nothingness. Planets, too, face a grim future. As stars age, their habitable zones, the regions where liquid water can exist, will shift outward, potentially rendering Earth like planets barren. In the case of our Sun, its eventual transformation into a red giant will scorch the inner planets, likely engulfing Mercury and Venus and stripping Earth of its atmosphere and oceans. Even in systems with stable stars, gravitational interactions will destabilize planetary orbits over immense timescales. Rogue planets, ejected from their systems, will wander the cold void of interstellar space. Moons and rings will be disrupted, either crashing into their parent planets or escaping altogether. The intricate dance of celestial bodies will unravel as entropy increases. Galaxies, majestic as they are, will also succumb to cosmic forces. The Milky Way and Andromeda are already on a collision course, set to merge in about 4.5 billion years. This galactic dance will create a new elliptical galaxy, but star formation will eventually wane as gas reserves are depleted. Over tens of billions of years, galaxies will become red and dead, dominated by aging stars with no fuel to create new ones. In the far future, galaxy clusters will drift apart, stretched by the accelerating expansion of the universe, driven by dark energy. The cosmic web, which now binds galaxies into vast filaments, will dissolve, leaving individual galaxies isolated in an ever-darkening cosmos. Without fresh material to sustain them, these galaxies will fade, their stars dimming and their black holes evaporating. The universe's ultimate fate hinges on the nature of dark energy. If the current acceleration continues indefinitely, we may face a big freeze where all energy is evenly distributed across an ever-expanding cosmos. In this scenario, stars will cease to shine, black holes will evaporate, and even subatomic particles may decay, leaving a featureless, cold void. Alternatively, if dark energy strengthens over time, the universe could end in a big rip. In this dramatic scenario, dark energy's repulsive force would overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. The universe would end in a cascade of destruction, with everything reduced to its most fundamental components. Yet, there is another possibility, a cosmic rebirth. Some theories suggest that the universe go through phases of expansion and contraction. In this Big Bounce model, the current expansion might reverse into a collapse, culminating in a new Big Bang and the birth of a fresh universe. While speculative, this idea offers a vision of a cosmos without a definitive end. As we gaze into the future of the universe, we are reminded of its vastness and complexity. From the fiery births of stars to the cold silence of black dwarfs, every phase of cosmic evolution tells a story of transformation and resilience. The atoms in our bodies, forged in the hearts of ancient stars, are part of this grand narrative. Even as the universe marches toward its ultimate fate, the legacy of its creation persists in every corner of existence. Would you like to explore the human connection to this cosmic story, or delve deeper into the mysteries of dark energy and alternate universes? Humanity's connection to the cosmos. Amid the grand scales of time and space, humanity's existence might seem fleeting and insignificant. Yet, our connection to the cosmos is profound. Every atom in our bodies was forged in the heart of a star, scattered across the galaxy by supernova explosions billions of years ago. We are, quite literally, made of stardust, a fact that binds us to the universe in the most fundamental way. As we gaze at the night sky, we're not merely looking at distant points of light, we're peering back in time. The light from the nearest stars takes years to reach us, while the light from distant galaxies has traveled billions of years across space. The stars we see are snapshots of the past, windows into the universe's history. This act of observation connects us to the origins of the cosmos and the forces that shaped it. Humanity's curiosity about the universe is as old as civilization itself. From ancient myths that sought to explain the patterns of the stars to modern telescopes that peer into the depths of the cosmos, our desire to understand the universe has driven scientific and cultural progress. The discovery that Earth is not the center of the cosmos, but merely one planet in a vast galaxy, and that our galaxy is just one among billions, has reshaped our perspective on existence. The modern era has brought unprecedented insights into the universe. Space exploration, from the Apollo moon landings to robotic missions to Mars, has expanded our physical presence beyond Earth. Telescopes like Hubble and the James Webb Space Telescope have revealed the universe's wonders in breathtaking detail, showing us star-forming nebulae, colliding galaxies, and even planets orbiting distant stars. These achievements are a testament to humanity's ingenuity and drive to uncover the unknown. Yet, as we explore the cosmos, we also reflect on our place within it. The discovery of exoplanets and habitable zones, worlds that could potentially host life, raises profound questions. Are we alone in the universe? If other civilizations exist, what might they look like? And how might we communicate with them? The search for extraterrestrial intelligence, SETI, continues to scan the skies for signals that could reveal the presence of other thinking beings. Beyond the scientific, the cosmos inspires awe and wonder. Its beauty, from the glowing arcs of the Milky Way to the fiery remnants of supernovae, stirs our imaginations and reminds us of our connection to something far greater than ourselves. Artists, poets, and philosophers have long drawn inspiration from the stars, weaving them into stories and symbols that define human culture. As stewards of Earth, humanity also faces the challenge of preserving our planet while looking to the stars. Space exploration offers the potential for survival beyond Earth, whether by establishing colonies on Mars or exploring the outer planet's moons. These endeavors could ensure the continuity of life, even as our sun ages and the conditions on Earth become less hospitable. Our journey into the cosmos is still in its infancy. Future generations may one day travel to distant stars, explore other galaxies, and uncover the universe's deepest mysteries. They may look back on this era as the moment humanity first took its steps into the vastness of space, a pivotal chapter in the story of intelligent life. But the ultimate question remains: what does it all mean? In a universe governed by physical laws and immense scales, does life hold a purpose beyond survival and curiosity? These are questions that transcend science, delving into the realms of philosophy and spirituality. Perhaps our connection to the cosmos lies not in seeking answers, but in embracing the mystery, finding meaning in the act of exploration itself. As we stand on this small blue planet, orbiting an average star in a galaxy among billions, we are reminded that our existence is both fragile and extraordinary. The universe, vast and indifferent, has given rise to beings capable of pondering its nature. This alone is a remarkable fact, one that ties us, irrevocably, to the stars. Would you like to delve into humanity's future role in the cosmos, the prospects of interstellar travel, or the philosophical implications of our cosmic origins? Humanity's future among the stars. As we contemplate humanity's future, the cosmos offers both a challenge and a promise. The Earth, while our cradle, is not a permanent haven. The forces that have shaped our planet and enabled life will, over geological and cosmic timescales, make it uninhabitable. The question is not whether humanity must one day look to the stars, but when and how we will do so. The first step in our journey beyond Earth is already underway. Robotic explorers like the Mars rovers and the Voyager spacecraft have extended humanity's reach into the solar system and beyond. These missions have revealed not only the stark beauty of other worlds, but also their potential as future homes. Mars, with its polar ice caps and evidence of ancient rivers, is the most immediate candidate for colonization. Efforts by agencies like NASA and private companies such as SpaceX aim to establish a human presence on the red planet within the coming decades. But Mars is only the beginning. Moons like Europa, Enceladus, and Titan offer tantalizing prospects for exploration. Europa, with its subsurface ocean beneath a crust of ice, could harbor microbial life, while Titan, with its thick atmosphere and lakes of liquid methane, presents a laboratory for studying prebiotic chemistry. These icy moons may one day host research outposts or even permanent habitats, pushing humanity further into the outer solar system. Beyond our solar system lies the ultimate frontier, the stars. The discovery of exoplanets in the habitable zones of distant stars has reignited dreams of interstellar travel. Systems like Proxima Centauri, only 4.24 light-years away, harbor planets that may resemble Earth. Reaching them, however, poses immense technological and logistical challenges. Current spacecraft would take tens of thousands of years to travel such distances, making advancements in propulsion systems essential. Concepts like nuclear fusion, antimatter drives, or even warp technology once relegated to science fiction are now being explored as potential solutions. The Breakthrough Starshot initiative, for instance, proposes using powerful lasers to propel tiny spacecraft at a fraction of the speed of light. Such missions could send probes to neighboring stars within a human lifetime, providing our first close-up look at alien worlds. But interstellar travel isn't just about technology, it's about survival. The Sun, while stable now, will eventually evolve into a red giant, making Earth uninhabitable. Humanity must either move to other planets or perish. Expanding into the galaxy is not merely a bold vision, it's an insurance policy for the continuation of intelligent life. Colonizing other star systems ensures that humanity and the legacy of Earth will endure. The philosophical implications of such a future are profound. As humanity spreads across the stars, our identity will inevitably change. Will we remain one species, united by a shared history, or will isolation lead to divergence, creating new forms of humanity adapted to different environments? Will the cultures and traditions we carry with us thrive on distant worlds, or will new ideas and values emerge in alien skies? There's also the question of how we'll interact with any other intelligent beings we might encounter. The discovery of extraterrestrial civilizations, whether through their signals or direct contact, would be a transformative moment in human history. It could bring answers to questions about our uniqueness, challenge our philosophies, or even reshape our technological and cultural trajectories. Interstellar travel also forces us to grapple with ethical considerations. What responsibilities do we have to preserve the ecosystems of other worlds? Should we prioritize exploring uninhabited planets to avoid potentially harmful encounters with alien life? These questions will shape the policies and principles of spacefaring civilizations. Humanity's journey into the cosmos will be defined not just by technological ingenuity, but by our ability to adapt, cooperate, and envision a shared destiny. As we extend our reach, we carry with us the dreams and aspirations of countless generations who looked up at the stars and wondered what lies beyond. The universe is vast, and the challenges are immense. but so too is the potential. With every step forward, from the moon landings to the exploration of distant planets, we reaffirm our place in the cosmic story. The stars are not just destinations, they are the next chapter in humanity's quest to understand its place in the universe. Shall we delve into the technologies required for interstellar travel, the ethics of planetary colonization, or the potential cultural impact of becoming a multiplanetary species? The technologies of interstellar travel. Reaching the stars requires technology that transcends anything humanity has ever built. The distances involved are staggering. Light, the fastest thing in the universe, takes over 4 years to reach our closest stellar neighbor, Proxima Centauri. To traverse these immense gaps, humanity must develop propulsion systems, energy solutions, and life support technologies that redefine the limits of engineering and science. Current propulsion systems, like chemical rockets, are effective for exploring our solar system, but hopelessly inadequate for interstellar travel. Even the fastest spacecraft built to date, the Parker Solar Probe, would take over 70,000 years to reach the nearest star. To make interstellar journeys feasible, we must achieve speeds that approach a significant fraction of the speed of light. One promising technology is nuclear fusion propulsion. Fusion, the same process that powers the sun, could provide the immense energy required to propel spacecraft at unprecedented speeds. Fusion engines would use isotopes like deuterium and tritium, extracted from water or other sources, to generate thrust through controlled nuclear reactions. While still in the experimental phase, fusion propulsion could theoretically reduce travel times to nearby stars to a few decades. Antimatter propulsion offers an even more extreme solution. Antimatter annihilates matter in a burst of pure energy, making it the most efficient fuel source imaginable. A spacecraft powered by antimatter could reach speeds close to 50% of the speed of light, cutting travel times to Proxima Centauri to less than a decade. However, producing and storing antimatter safely is a monumental challenge, as even a small amount could release catastrophic energy. Another concept, the laser sail, is being actively explored by initiatives like Breakthrough Starshot. This approach involves equipping spacecraft with ultra-thin sails that reflect powerful laser beams from Earth or orbiting stations. The lasers would propel the spacecraft to speeds exceeding 20% of the speed of light. Such probes could reach the nearest stars in just a few decades, though this technology is currently suitable only for small, lightweight payloads. More speculative technologies include warp drives and wormholes, inspired by theoretical physics and popularized by science fiction. A warp drive, based on Einstein's general theory of relativity, would involve bending spacetime to allow a spacecraft to move faster than light relative to its surroundings. While this idea remains highly theoretical, advancements in understanding exotic materials and energy might one day bring it closer to reality. For interstellar travel to be practical, energy solutions must also evolve. Spacecraft capable of sustaining long journeys will need power sources that can operate independently for decades or centuries. Compact nuclear reactors, advanced solar arrays, or even harnessing energy from the interstellar medium could provide the necessary power for propulsion, life support, and onboard systems. Life support technology presents another critical challenge. Human passengers on interstellar missions will need a stable environment for decades, perhaps centuries. Closed-loop systems capable of recycling air, water, and waste indefinitely are essential. Advances in biotechnology, such as growing food in microgravity or engineering self-sustaining ecosystems, could make long-duration space travel viable. Artificial intelligence, AI, will play a pivotal role in interstellar missions. AI systems can monitor spacecraft, make real-time decisions, and ensure the well-being of passengers. Autonomous AI probes could also be sent ahead of human explorers to map star systems, identify habitable planets, and prepare the way for colonization. Interstellar travel isn't just about speed or endurance, it's also about communication. Sending signals across light years introduces significant delays, making real-time communication impossible. Advanced technologies, such as quantum entanglement for instantaneous data transfer or highly efficient long-range radio systems, will be essential for maintaining contact with Earth and coordinating missions. Despite the immense challenges, the pursuit of interstellar travel embodies humanity's spirit of exploration and innovation. It represents a leap not only in technology but in our understanding of what is possible. Each step forward, from refining propulsion systems to creating sustainable habitats, brings us closer to realizing the dream of reaching other stars. The technologies needed for interstellar journeys will transform not just space travel but life on Earth. Fusion power could solve energy crises, advanced recycling systems could revolutionize sustainability, and AI developed for space exploration could enhance countless industries. The pursuit of the stars, far from being a distant dream, has practical implications that will benefit humanity long before the first interstellar mission launches. Next, let's explore the ethics and responsibilities of venturing into space. How should humanity approach the colonization of other worlds? What principles should guide our interactions with alien ecosystems or civilizations? The symphony of gravitational waves, echoes of the universe. The universe is not silent. Though space is a vacuum where sound cannot travel, it vibrates with an invisible symphony. Gravitational waves, ripples in the fabric of space-time itself. These waves, predicted by Albert Einstein over a century ago, are the echoes of some of the most violent and spectacular events in the cosmos. They are the universe's whispers, carrying tales of its hidden wonders. Gravitational waves are produced whenever massive objects accelerate, but only cataclysmic events such as the collision of black holes, the explosion of supernovae, or the merging of neutron stars create waves powerful enough to detect. These ripples propagate at the speed of light, stretching and compressing space as they pass through. Imagine tossing a stone into a still pond. The ripples spreading outward are a two-dimensional analogy of these cosmic disturbances. For decades, gravitational waves existed only as a theoretical concept. Then, in 2015, humanity finally heard the faint chirp of spacetime itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected waves from the merger of two black holes 1.3 billion light-years away. This groundbreaking observation confirmed Einstein's theory and opened a new window into the universe. Unlike light, which can be blocked by dust and gas, gravitational waves travel unobstructed through the universe, carrying information about their sources that no other signals can provide. They reveal events hidden from traditional telescopes, allowing us to observe phenomena like the formation of black holes or the collision of dense neutron stars that produce heavy elements like gold and platinum. But the story of gravitational waves is just beginning. Advanced detectors like Virgo and the planned space-based observatory LISA, Laser Interferometer Space Antenna, promise to uncover even more. LISA, with its enormous arms stretching millions of kilometers, will detect lower frequency waves from supermassive black hole mergers and other cosmic marvels. These instruments will transform our understanding of the universe, revealing secrets that were once beyond our reach. Gravitational waves also carry the potential to answer some of the deepest questions about the cosmos. Could they reveal the dynamics of the first moments after the Big Bang? If primordial gravitational waves exist, they would hold the fingerprints of inflation, the rapid expansion of the universe in its infancy. Detecting these waves would provide direct evidence of the universe's birth and the forces that shaped it. Even more tantalizing is the possibility that gravitational waves could uncover entirely new phenomena. Exotic objects like boson stars, hypothetical entities made of dark matter particles, might produce unique gravitational wave signatures. Similarly, waves from cosmic strings, hypothetical defects in space-time, could hint at physics beyond the standard model, offering clues about the unification of forces or the existence of extra dimensions. Gravitational wave astronomy is not just a tool for observing the universe, it is a way of listening to it. Each detected wave is a piece of a cosmic symphony, a story of creation, destruction, and transformation. These waves connect us to the most extreme events in the cosmos, from black holes spinning in a deadly embrace to neutron stars colliding in fiery bursts that outshine entire galaxies. The idea that the universe sings in its own way sparks imagination. Could advanced civilizations be listening to gravitational waves, using them to communicate across cosmic distances? Might the patterns of these waves encode messages from the distant past or clues about the universe's future? Such possibilities challenge us to think not just scientifically but creatively about the cosmos and our place within it. As we develop better tools to detect and interpret gravitational waves, we are reminded of the interconnectedness of all things. These waves ripple through space-time, linking us to events billions of years and light-years away. In their gentle stretching and compressing of reality, They tell a story not just of the universe's grandest moments, but of its fundamental nature. Let's now shift to another profound and mysterious phenomenon: the role of time in the universe. What is time's true nature? Is it a fundamental aspect of reality, or could it be an illusion, a construct of human perception? Shall we journey into the enigma of time and its connection to the cosmos? The enigma of time, the universe's invisible thread. Time is the silent companion of the universe, ever-present yet elusive, a dimension as fundamental as space itself. It governs the rhythm of the cosmos, from the birth and death of stars to the expansion of galaxies and the evolution of life. But what is time really? Is it a universal constant, flowing like a river, or is it something more fluid, tied to the observer's perspective and the universe's mysterious fabric? Albert Einstein revolutionized our understanding of time by showing that it is not an independent entity, but deeply intertwined with space. Together they form spacetime, a dynamic, malleable fabric shaped by the presence of mass and energy. This insight, encapsulated in Einstein's theory of general relativity, revealed that time is not absolute. It can stretch, compress, and even slow to a crawl under the right conditions. One of the most striking demonstrations of this is gravitational time dilation. Near massive objects like black holes, space-time is warped so severely that time itself slows down. If you were to orbit close to a black hole, while your twin remained on Earth, you would age more slowly than your sibling. This isn't just a thought experiment, it's a real phenomenon. Astronauts on the International Space Station experience time slightly differently than those on Earth due to the weaker gravitational field and their high-velocity effects measured with astonishing precision. Time dilation also occurs at high speeds, as described by Einstein's special theory of relativity. As an object approaches the speed of light, time slows for it relative to an outside observer. If a spacecraft could travel at near light speeds, its crew might experience a journey of only a few years while centuries pass for those left behind. This relativistic time travel is not science fiction, but a consequence of the universe's structure, with profound implications for interstellar exploration. But time's mysteries go beyond relativity. At the smallest scales, in the realm of quantum mechanics, time behaves in strange and unexpected ways. Particles can exist in superpositions, where their states seem undefined until observed, raising questions about whether time flows smoothly or jumps in discrete intervals. The interplay between quantum mechanics and relativity remains one of physics' greatest puzzles, hinting at deeper truths about time's nature. The arrow of time, the fact that it moves forward, not backward, is another enigma. In most physical laws, time is symmetric. There's nothing in the equations that prevents it from running in reverse. Yet, in our everyday experience, time flows irreversibly. This asymmetry is linked to entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy tends to increase, giving time its forward direction. But why did the universe start in a state of such low entropy, allowing for this forward flow? This question ties time to the very origins of the cosmos. Some theories suggest that time itself may be an emergent property, not a fundamental aspect of reality. In this view, time arises from deeper, timeless laws of physics, much like temperature emerges from the motion of molecules. If this is true, our perception of time as a continuous flow might be an illusion, a construct of consciousness shaped by the brain's need to process and sequence events. Time also raises profound philosophical and existential questions. Is the past fixed and the future open? Or do all moments exist simultaneously, as some interpretations of relativity suggest? If time is infinite, what does that mean for the universe's destiny? Could cycles of time exist, where the end of one universe gives birth to another? Such ideas challenge our understanding of causality and reality itself. On a cosmic scale, time governs the universe's evolution. It measures the age of stars and galaxies, the lifespans of black holes, and the endless expansion driven by dark energy. Yet, as the universe expands and cools, time's role may shift. In a far distant future, when stars have burned out and black holes have evaporated, will time lose its meaning in a cold, empty void? Or will new physical laws emerge, rewriting the story of time itself? Time is not just a physical phenomenon, it is a deeply human experience. It shapes our lives, memories, and dreams. It is the canvas on which we paint the stories of our existence, the measure of moments both fleeting and eternal. To understand time is to understand the universe and ourselves. Shall we now explore time travel and its possibilities in science and fiction, or dive deeper into the mysteries of cosmic origins and time's role in the birth of the universe? The possibility of time travel, a journey through reality and imagination. Time travel has long been a fascination of human imagination, a concept explored in countless books, films, and scientific theories. The idea of stepping into the past or leaping into the future evokes both wonder and profound questions about causality, free will, and the nature of the universe itself. But how much of this is grounded in science? Could time travel ever be more than a fictional dream? Einstein's theory of relativity provides a foundation for the possibility of time travel at least to the future. As we've seen, traveling at speeds near the speed of light slows time for the traveler relative to outside observers. This form of time dilation allows for a kind of one-way trip into the future. A person traveling at relativistic speeds could experience a journey lasting mere years, while centuries pass for those back home. This isn't just theoretical. Experiments with high-speed particles and atomic clocks have confirmed time dilation's effects on small scales. But what about traveling to the past? This is where the science becomes more speculative. General relativity suggests that certain space-time configurations could allow for closed time-like curves paths that loop back on themselves, enabling backward time travel. Wormholes, hypothetical tunnels through space-time, have often been proposed as potential time machines. If a wormhole's ends were connected to different points in time, traversing it might allow someone to emerge in the past. Theoretical physicist Kip Thorne famously explored this concept, proposing that a traversable wormhole could be created if exotic matter with negative energy existed to stabilize it. However, this idea faces enormous practical and theoretical hurdles, not least of which is the question of whether exotic matter is even possible. Another speculative concept is the use of cosmic strings' hypothetical one-dimensional defects in space-time to create a time loop. If two cosmic strings passed near each other at nearly the speed of light, their immense gravitational fields might distort space-time enough to permit backward travel. Similarly, rotating black holes, or Kerr black holes, might theoretically allow for paths through space-time that could lead to the past. Yet, all these ideas encounter significant challenges. Time travel to the past raises paradoxes, such as the classic grandfather paradox, where a time traveler's actions could prevent their own existence. Some theories suggest that these paradoxes might be resolved by the concept of self-consistency. The past cannot be changed, and any actions taken by a time traveler would already be part of history. Others propose the multiverse hypothesis, where changes to the past create alternate timelines rather than altering the original one. Quantum mechanics offers another angle on time travel. The concept of quantum superposition and the probabilistic nature of particles have led some physicists to speculate about quantum time travel, where particles might influence events in their own past. However, these ideas are far from proven and remain in the realm of theoretical speculation. Despite the challenges, time travel has inspired serious scientific exploration. Not because we expect to build a time machine tomorrow, but because studying the concept pushes the boundaries of our understanding of physics. Time travel theories intersect with questions about the nature of space-time, causality, and the unification of quantum mechanics and general relativity. They force us to confront the limits of our knowledge and consider possibilities that challenge our intuitions about reality. Beyond the science, time travel captivates our imaginations because it speaks to deeply human desires, the wish to undo past mistakes, to revisit cherished moments, or to glimpse what lies ahead. It also raises profound ethical and philosophical questions. If time travel were possible, who would have the right to wield such power? How would it affect our perception of history and our responsibility to the future? While practical time travel may remain out of reach, its exploration continues to expand our horizons. It challenges us to think beyond the present, to imagine a universe where time is not a boundary but a dimension to be navigated. And even if we never build a time machine, the very act of contemplating time travel brings us closer to understanding the true nature of time itself. Shall we now dive into the multiverse theory, exploring the possibility of parallel universes and alternate timelines, or shift focus to the ultimate fate of the universe as we unravel its greatest mysteries? The multiverse, parallel universes and alternate realities. Beyond our observable universe lies a tantalizing possibility, the existence of a multiverse, a vast collection of universes where alternate realities, different laws of physics, and unimaginable phenomena unfold. The multiverse theory, once the domain of science fiction, has gained traction in theoretical physics as scientists attempt to address profound questions about the nature of reality and the origins of the cosmos. The idea of the multiverse arises naturally from several lines of scientific inquiry. One of the most compelling comes from the concept of cosmic inflation, the rapid expansion of the universe in its earliest moments. Inflation theory suggests that while our observable universe expanded and cooled into the structure we see today, other regions of spacetime could have undergone their own inflationary processes. These regions, separated from our own by vast distances or barriers in spacetime, might constitute entirely distinct universes, each with its own properties and physical laws. This version of the multiverse, known as the bubble universe model, envisions each universe as a bubble in a vast cosmic foam. Some bubbles may resemble our own, while others could be radically different, with alternate values for fundamental constants like the speed of light or the strength of gravity. In some universes, stars might never form; in others, entirely novel phenomena might emerge. Another perspective on the multiverse comes from quantum mechanics, specifically the many worlds interpretation. According to this interpretation, every quantum event, every decision, every measurement branches into multiple outcomes, each realized in a separate universe. In this view, the multiverse is not a collection of distant cosmic bubbles, but an ever-expanding tree of possibilities, where every what-if plays out in its own timeline. Imagine a world where you chose a different career, where ancient civilizations never fell, or where the dinosaurs never went extinct. These parallel realities, while speculative, offer a fascinating lens through which to consider the nature of choice, causality, and existence itself. String theory, another cornerstone of modern theoretical physics, also hints at a multiverse. This theory posits that the fundamental particles of the universe are not points but vibrating strings, with their properties determined by the way they vibrate. The equations of string theory suggest that there are many possible configurations of spacetime, possibly as many as 105, 001, 0501, 500 distinct vacua. Each of these configurations could represent a unique universe within the multiverse, governed by its own version of physical laws. The multiverse theory raises profound philosophical and scientific questions. If other universes exist, can we ever observe them? Could there be a way to interact with or even travel between universes? And what does the existence of a multiverse mean for our understanding of reality and our place within it? Some physicists argue that the multiverse is an inevitable consequence of current theories, while others criticize it for being untestable, straying from the realm of empirical science into speculation. Despite these debates, the multiverse has captivated imaginations across disciplines. It challenges our assumptions about the uniqueness of our universe and forces us to consider the possibility that our reality is just one small piece of a much larger puzzle. It also provides potential answers to some of the universe's greatest mysteries, such as why the laws of physics in our universe seem so finely tuned to allow for the existence of life. In a multiverse, such fine-tuning might be explained by the simple fact that we happen to live in a universe where conditions are just right, one of countless possibilities. The implications of the multiverse extend beyond science. They touch on profound existential questions. If there are infinite versions of reality, what does it mean to be you? Does the existence of other universes diminish the significance of our own? Or does it amplify it, highlighting the extraordinary chance that we exist here and now? As we ponder the multiverse, we are reminded of the boundless creativity of the cosmos. Whether or not parallel universes exist, the very idea expands our horizons, encouraging us to think beyond the limits of the observable and imagine what might lie beyond. Shall we explore the relationship between the multiverse and the origins of the universe, or turn our focus to another mind-bending concept, the possibility of life in these alternate realities and what it might mean for the search for extraterrestrial intelligence? The possibility of life in the multiverse. If the multiverse is real, it raises one of the most profound questions of all. Could life exist in these alternate realities? The idea that life might not only inhabit our universe, but countless others expands the scope of the search for extraterrestrial intelligence to a cosmic level, redefining what we mean by life and existence. In our universe, life depends on a delicate balance of physical constants. The strength of gravity, the charge of the electron, the nuclear forces that hold atoms together, all are fine-tuned within narrow ranges that allow stars to burn, molecules to form, and chemistry to flourish. If even one of these constants were slightly different, life as we know it might be impossible. This fine-tuning, often referred to as the anthropic principle, has led some to suggest that our universe is uniquely suited for life. But in a multiverse, the fine-tuning problem takes on a new dimension. In the bubble universe model, each universe could have different physical constants and laws. While many might be inhospitable to life, others might host conditions even more favorable than our own. Imagine a universe where stars live longer, where complex chemistry arises more easily, or where entirely new forms of matter and energy enable life unlike anything we can conceive. Life in these universes might not be carbon-based, might not rely on water, or might not even exist in physical space as we understand it. The possibilities are as vast as the multiverse itself. The many worlds interpretation of quantum mechanics adds another layer of complexity. In this view, every quantum event branches into multiple realities, creating countless versions of history. If true, there could be universes where humanity has already discovered advanced technologies, where civilizations long extinct in our timeline continue to thrive, or even where life evolved in completely different ways. Some of these parallel worlds might be nearly indistinguishable from ours, while others might be alien in every sense of the word. The search for life in the multiverse forces us to rethink the definition of life itself. In our universe, life is often defined by its ability to grow, reproduce, and adapt to its environment. But what if, in other universes, life takes forms that defy these criteria? Could there be entities made entirely of energy, sentient patterns in space-time? Or even forms of life that exist outside of time and space as we understand them? The multiverse opens the door to these possibilities, challenging our assumptions and expanding the scope of the search for intelligence. The implications of multiverse life are profound. If intelligent beings exist in other universes, could they be aware of us? Could they have found ways to traverse the barriers between universes, making contact with our own? Some scientists speculate that advanced civilizations might manipulate gravitational waves, quantum entanglement, or other exotic phenomena to bridge the gap between realities. If so, the multiverse might not just be a collection of isolated bubbles, but a network of interconnected worlds. From a philosophical perspective, the existence of life in the multiverse raises questions about the uniqueness of our existence. Are we one of countless intelligent civilizations scattered across an infinite array of universes, or is life in any form exceedingly rare, even in a multiverse? If life exists in multiple universes, does that diminish the significance of our own? Or does it enhance it, showing that the cosmos in all its vastness is fertile ground for creation and diversity? Even without direct evidence, the concept of life in the multiverse inspires scientific and imaginative exploration. It pushes us to develop new theories, new tools, and new ways of thinking about the cosmos. It encourages us to look beyond the boundaries of what we know and consider the extraordinary possibilities that lie beyond. As we reflect on the potential for life in the multiverse, another question emerges. What role does our own universe play in this grand tapestry? Is it one of many equally significant realities, or does it hold a special place in the multiverse? Shall we delve into the philosophical implications of our universe's role in the multiverse, or explore how these ideas influence the search for life within our own cosmic boundaries? The role of our universe in the multiverse. If the multiverse exists, it's natural to wonder, what makes our universe special, or is it special at all? Are we merely one among countless realities, each equally significant, or does our universe hold a unique position in this vast cosmic ensemble? The question touches not only on science but also on philosophy, theology, and the very essence of human existence. One perspective suggests that our universe is unremarkable, simply one bubble in a cosmic foam, or one branch of an infinite quantum tree. This viewpoint aligns with the Copernican principle, which asserts that humanity occupies no privileged position in the cosmos. Just as Earth was revealed to be one planet among many, our universe might be just one of countless others, its features dictated by chance rather than design. Yet, even in this context, our universe is special to us. It is the universe where we exist, where the conditions for life have aligned so precisely that intelligent beings can ponder these mysteries. This is the essence of the anthropic principle. Our universe is observable precisely because it allows observers to exist. In a multiverse, this principle might explain why our universe appears so finely tuned. Among countless universes, we happen to live in one where the conditions support life. But what if our universe is special, not just to us but in the grander scheme of the multiverse? Some theories propose that our universe might play a unique role, such as being a seed for other universes. In speculative models of eternal inflation, universes can spawn new universes through processes akin to cosmic reproduction. If our universe has the right properties, it could serve as a cosmic parent, giving rise to other bubbles in the multiverse. Alternatively, our universe might be a kind of experiment intentionally or unintentionally created. Some physicists have speculated about the possibility of advanced civilizations creating universes through sophisticated manipulation of physics. If this is the case, our universe might exist as part of a grand cosmic design, its laws of nature chosen or optimized for specific outcomes. The concept of the multiverse also raises questions about the ultimate purpose or lack thereof of existence. Is the multiverse a random, infinite playground where every possibility is realized, or does it follow underlying principles that govern its structure? If there are infinite universes, does anything truly matter? Or does the very existence of infinity enhance the significance of each individual moment, including ours? The relationship between our universe and the multiverse also intersects with ideas from quantum mechanics and information theory. Some theorists suggest that our universe might be a simulation, a detailed computational construct created by an advanced intelligence. If simulations can exist, the multiverse might include layers of realities, each capable of simulating others, creating a hierarchy of universes within universes. From a philosophical perspective, the multiverse challenges deeply held notions about identity, uniqueness, and the meaning of existence. If every possible version of events occurs somewhere in the multiverse, what does that mean for free will and choice? Are our decisions meaningful if alternate versions of us are living out every possible outcome? Or does this multiplicity enrich our understanding of existence, showing that every action contributes to a vast, interconnected whole? Ultimately, our universe's role in the multiverse, if such a concept exists, remains one of the greatest mysteries in science. Whether we are a single drop in an infinite sea or a singular phenomenon, the very act of contemplating our place in the cosmos is a testament to the power of human curiosity and imagination. Shall we now explore the philosophical implications of an infinite multiverse, or shift focus to the science and technology needed to uncover evidence of other universes? Alternatively, we could delve into how these ideas influence humanity's quest for meaning in the vast expanse of the cosmos. The philosophical implications of an infinite multiverse. The concept of an infinite multiverse is as humbling as it is provocative. It challenges our understanding of existence, identity, and purpose, raising questions that bridge science, philosophy, and even spirituality. If there are infinite universes where every possibility is realized, what does that mean for our lives, our choices, and our sense of self? One of the most profound implications of an infinite multiverse is the idea that every possible version of events occurs somewhere. In this vast ensemble, there could be universes where history unfolded differently, where dinosaurs never went extinct, where humanity developed interstellar travel millennia ago, or where the laws of physics took entirely alien forms. This raises a disquieting question. If every possibility is realized, do our decisions matter? The many worlds interpretation of quantum mechanics amplifies this dilemma. If every quantum event branches into a new reality, there are countless versions of you, each living out a different outcome of your choices. In one universe, you might have chosen a different career, met different people, or avoided a critical mistake. These alternate selves blur the line between individuality and universality, suggesting that you are not confined to a single timeline but exist across countless realities. This multiplicity forces us to confront the nature of free will. If every choice leads to all possible outcomes somewhere, is free will an illusion? Or does it gain deeper meaning in the context of the multiverse? Some philosophers argue that the existence of multiple outcomes doesn't diminish the significance of individual choices, but instead highlights their role in shaping the tapestry of reality. The infinite multiverse also touches on questions of identity and uniqueness. Are you the only you, or are there countless versions of yourself, each equally real? If you are not unique, does that make your existence less significant? Or does it underscore the miraculous nature of being aware in this particular universe at this particular moment? The multiverse invites us to redefine what it means to be one of a kind in a cosmos where infinite variations of every being and event might exist. From a spiritual perspective, the multiverse could offer new interpretations of ancient ideas. Concepts like reincarnation, karma, or even divine omnipresence take on new dimensions in a multiverse framework. Could the existence of infinite realities align with notions of eternal cycles or infinite potential? Could each universe represent a facet of a greater, interconnected whole? Ethical questions also arise. If infinite versions of reality exist, does that reduce the moral weight of our actions? Does the existence of a universe where everything went right absolve us of responsibility for our mistakes? Or does it place greater emphasis on living meaningfully in the universe we inhabit, knowing that our choices shape not just our lives but the very reality around us? The multiverse also challenges traditional notions of purpose and destiny. If there are infinite universes, is there a grand design, or is existence a cosmic accident? Some argue that the multiverse suggests a purposeless cosmos, where every possibility is realized simply because it can be. Others find meaning in the multiverse's vastness, seeing it as a reflection of infinite potential and creativity. For humanity, the multiverse offers an opportunity to expand our perspective. It reminds us that our universe, while vast and wondrous, might be one small part of an even grander reality. This realization encourages humility, curiosity, and a deeper appreciation for the mystery of existence. Whether or not we ever uncover direct evidence of other universes, the very idea pushes us to think beyond the boundaries of the observable and embrace the unknown. Shall we now explore the scientific quest for evidence of the multiverse, examining how physics and technology might one day confirm or refute its existence? Or would you like to delve into the practical implications of these ideas for humanity's future in space exploration and understanding of reality? The scientific quest for evidence of the multiverse. The multiverse, while a captivating concept, remains largely theoretical, but science thrives on turning the speculative into the observable. Physicists and cosmologists are actively seeking evidence that might confirm or refute the existence of other universes, transforming what was once the realm of imagination into a serious scientific endeavor. The journey to uncover the multiverse requires innovation in theory, experimentation, and technology. One potential clue lies in the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates our universe. The CMB is a snapshot of the universe when it was just 380,000 years old, and its temperature fluctuations provide insights into the conditions of the early cosmos. Some physicists suggest that if our universe has collided with another bubble universe in the past, the imprint of this collision might be visible as subtle anomalies in the CMB, unusual cold, or hot spots that deviate from the standard model of cosmology. Efforts to detect such anomalies are ongoing. Instruments like the Planck satellite and upcoming missions AIMS-ENB with increasing precision, searching for telltale patterns that could hint at interactions with other universes. While no definitive evidence has been found yet, the search continues to refine our understanding of the universe's origins. Gravitational waves also hold promise for uncovering the multiverse. These ripples in spacetime, first detected by LIGO in 2015, are produced by violent cosmic events like black hole mergers. Some theories predict that collisions between bubble universes during the inflationary period of the cosmos could generate unique gravitational wave signatures. Advanced detectors like LISA, Laser Interferometer Space Antenna, might one day pick up these primordial waves, offering direct evidence of other universes. Another avenue of investigation involves string theory, which posits that the fundamental particles of the universe are tiny vibrating strings. String theory predicts the existence of multiple dimensions beyond the familiar three of space and one of time, and it allows for a vast number of possible configurations of space-time. If these configurations correspond to different universes, evidence of higher dimensions or exotic particles might hint at the multiverse's existence. Particle physics experiments, such as those conducted at the Large Hadron Collider, LHC, are also probing the boundaries of reality. By smashing particles together at nearly the speed of light, scientists explore conditions that mimic the early moments of the universe. Some theories suggest that certain interactions could produce miniature black holes or other phenomena that hint at the existence of parallel universes. While such results have yet to be observed, each experiment pushes the boundaries of what we know. Quantum mechanics, too, offers intriguing possibilities. The many worlds interpretation suggests that every quantum decision creates a new branch of reality. While this idea remains untestable for now, future advancements in quantum computing and quantum communication might provide insights into whether alternate timelines exist and whether they can be accessed or influenced. One of the most ambitious ideas for probing the multiverse involves using advanced simulations and artificial intelligence. By creating detailed models of cosmic inflation in the early universe, scientists can explore how different physical parameters might give rise to other universes. These simulations could help identify signatures that would indicate the presence of a multiverse and guide observational efforts. Yet, the search for the multiverse faces significant challenges. By definition, other universes might be causally disconnected from ours, making direct observation impossible. Critics argue that without testable predictions, the multiverse remains more of a philosophical construct than a scientific theory. Proponents counter that the multiverse is a natural consequence of well-established theories like inflation and string theory, and its exploration is a logical extension of these frameworks. The pursuit of the multiverse is as much about pushing the limits of human knowledge as it is about finding definitive answers. Whether or not we ever detect another universe, the effort itself deepens our understanding of physics, cosmology, and the fundamental nature of reality. It challenges us to ask bigger questions, develop new technologies, and expand the horizons of science. As we explore these scientific frontiers, we're left with a profound realization. The quest for the multiverse is also a quest for understanding our place in the cosmos. Shall we now delve into how humanity might use these insights to redefine its future, from philosophical perspectives to practical applications in space exploration and technology? Or should we explore how these ideas influence our search for meaning in an infinite cosmos? Redefining humanity's future. Insights from the multiverse. The pursuit of understanding the multiverse not only broadens the boundaries of science, but also reshapes humanity's vision for the future. By exploring the possibility of multiple universes, we confront questions about our place in the cosmos, the purpose of existence, and how these revelations can inspire practical advancements in technology, space exploration, and society itself. A new cosmic perspective. The multiverse concept forces us to view our universe as one among countless others. This realization, like the Copernican revolution that showed Earth is not the center of the solar system, expands our perspective on existence. It humbles us by highlighting the vastness of reality while simultaneously emphasizing the uniqueness of our experiences in this particular universe. In a multiverse where infinite possibilities exist, every moment takes on profound significance. The choices we make, the paths we follow, and the ideas we pursue contribute to the tapestry of one specific reality. This awareness inspires a deeper appreciation for the fleeting beauty of life and encourages us to approach the unknown with curiosity and courage. Driving technological innovation. The scientific pursuit of the multiverse is pushing the limits of technology. Advanced telescopes, gravitational wave detectors, and quantum computers are all byproducts of this quest, with applications far beyond cosmology. These tools are not only unraveling the mysteries of the universe, but are also revolutionizing industries on Earth, from medicine to artificial intelligence. For instance, quantum computing, driven by research into the multiverse and quantum mechanics, has the potential to solve complex problems in cryptography, logistics, and climate modeling. Gravitational wave technology, initially developed to study cosmic phenomena, could lead to breakthroughs in seismic monitoring and early warning systems for natural disasters. The technologies inspired by the multiverse remind us that the pursuit of abstract questions often yields tangible benefits. Expanding the horizons of space exploration. The multiverse theory aligns naturally with humanity's aspirations for space exploration. If our universe is one of many, the drive to explore becomes not just a practical endeavor but a philosophical imperative. Colonizing other planets and venturing to distant star systems allows us to extend the reach of our reality, ensuring the survival and evolution of intelligent life. Insights from multiverse research might also inform the search for habitable exoplanets and extraterrestrial life. By understanding the conditions that make our universe conducive to life, we can better identify similar conditions in other star systems. Tools like the James Webb Space Telescope and future missions to study exoplanet atmospheres are stepping stones in this journey. In the distant future, if humanity masters interstellar travel, the multiverse might inspire even more ambitious goals, exploring alternate dimensions or parallel timelines. While these ideas remain speculative, they challenge us to think beyond the limits of current technology and consider what might one day be possible. The search for meaning in an infinite cosmos. An infinite multiverse challenges traditional notions of purpose and significance. If every possibility exists somewhere, what does it mean to be here, in this specific moment, in this particular universe? Far from rendering life meaningless, the multiverse invites us to find meaning in the act of discovery, in the relationships we build, and in the contributions we make to our shared reality. The concept of the multiverse also intersects with spiritual and philosophical traditions. Many belief systems emphasize the interconnectedness of all things, a notion that resonates with the idea of an infinite web of universes. The multiverse encourages a broader perspective on existence, one that transcends individual experience and embraces the vastness of reality. Humanity's role as cosmic explorers. The quest to understand the multiverse positions humanity as explorers not just of space and time, but of existence itself. This role carries immense responsibility: to seek knowledge with humility, to preserve the fragile ecosystems of our own world, and to approach the unknown with both scientific rigor and ethical awareness. As we venture further into the cosmos, inspired by the possibilities of the multiverse, we are reminded that exploration is as much an inward journey as it is an outward one. By striving to understand the cosmos, we come to understand ourselves, our origins, our potential, and our connection to a reality far greater than we can imagine. Shall we now delve into the ethical implications of space exploration in the context of the multiverse, or explore how humanity might prepare for a future where these theories reshape our understanding of reality and society? The ethical imperatives of space exploration in a multiverse. As humanity looks to the stars, the ethical implications of space exploration take on a profound importance. In the context of the multiverse, where infinite possibilities may exist, the decisions we make today about how we interact with our own universe and potentially others carry a weight that transcends time and space. How we approach this responsibility could define not only our future but also the legacy of intelligent life. The first ethical challenge lies in how we treat the ecosystems of other planets and moons within our solar system. Even in a single universe, the discovery of microbial life or prebiotic conditions on Mars, Europa, or Enceladus would demand a re-evaluation of our place in the cosmos. In a multiverse where life might take on countless forms, this consideration expands exponentially. Preserving alien ecosystems, even at the microbial level, becomes a question of respect for the natural processes that shape life, regardless of its origin. Human colonization of other planets introduces additional complexities. While the survival of humanity may depend on establishing self-sustaining colonies beyond Earth, this effort must balance the needs of future generations with the preservation of alien worlds. Should we terraform Mars or adapt ourselves to live in harmony with its natural environment? Would altering the climate of a distant planet to make it habitable violate its intrinsic value, even if no life exists there? If we someday encounter intelligent extraterrestrial civilizations, the stakes become even higher. In a multiverse where advanced civilizations might be common, the protocols we establish for first contact could ripple across realities. How should we approach beings with their own histories, cultures, and possibly vastly different ways of perceiving existence? Avoiding the mistakes of colonialism and exploitation that have marked humanity's past will require a level of humility and foresight unprecedented in human history. Exploring the multiverse, should it prove accessible, magnifies these ethical concerns. If alternate universes are discovered, would humanity have the right to interact with or influence them? What responsibilities would we have toward beings or civilizations in other realities? Could the act of observing or entering another universe inadvertently alter its trajectory? And if so, how might we mitigate such impacts? These questions force us to confront the limits of our understanding and the potential consequences of our actions on an infinite scale. The ethics of exploration also extend to humanity's relationship with its own technology. The development of advanced AI, fusion propulsion, and other cutting-edge technologies must be guided by principles that prioritize safety, sustainability, and the well-being of both humans and the environments we explore. Unchecked technological advancement, driven purely by ambition or competition, risks not only ecological and societal collapse, but also a potential loss of the values that make exploration meaningful. Ultimately, the multiverse concept challenges us to think beyond the immediate and the local. It encourages a perspective that values cooperation over competition, preservation over exploitation, and curiosity over conquest. If humanity is to become a spacefaring species and possibly a multiverse-faring one, it must do so with a commitment to principles that honor the diversity, complexity, and wonder of the cosmos. As we ponder these ethical considerations, the deeper question remains: how can humanity prepare for a future where these responsibilities become reality? What steps must we take to ensure that our journey into the cosmos is not just an expansion of territory but an expansion of understanding, empathy, and purpose? Preparing humanity for a cosmic future. Humanity's journey into the cosmos is no longer a distant dream but an emerging reality. As we step into this new era, preparing for a cosmic future requires more than technological advancement. It demands a holistic transformation, scientific, cultural, and ethical, that equips us to navigate the complexities of exploring the universe while safeguarding the values that define us. The first step is fostering a mindset of unity and collaboration. Space exploration transcends national borders and cultural differences, offering an opportunity to view humanity as a singular entity bound by a shared curiosity about the cosmos. Global cooperation, exemplified by endeavors like the International Space Station and the Artemis Accords, must be expanded to ensure that the benefits of exploration are shared by all. This collaboration should extend to addressing terrestrial challenges, climate change, resource scarcity, and inequality that threaten to undermine humanity's capacity to reach the stars. Education is another cornerstone of preparation. Inspiring future generations with the wonder of the cosmos will ensure that space exploration remains a priority. Schools and universities should integrate astrophysics, planetary science, and astrobiology into their curricula, encouraging students to think critically about humanity's role in the universe. Public outreach initiatives, such as planetariums, documentaries, and citizen science projects, can ignite widespread interest and support for cosmic endeavors. Technological innovation must advance responsibly. While propulsion systems, life support technology, and AI are essential for space exploration, their development should prioritize sustainability and ethical considerations. For instance, mining asteroids for resources could revolutionize industry while preserving Earth's environment, but it must be regulated to avoid overexploitation. Similarly, AI systems designed for space missions should be transparent, accountable, and aligned with humanity's goals and values. Preparing for the psychological and societal challenges of space exploration is equally vital. Long-duration missions to other planets or even other star systems will place immense strain on astronauts, requiring advancements in mental health support, team dynamics, and conflict resolution. On a societal level, humanity must grapple with the philosophical implications of venturing beyond Earth. How will leaving our home planet change our identity as a species? What cultural, artistic, and spiritual traditions will we carry into the cosmos? And how will they evolve in new environments? The potential discovery of extraterrestrial life or contact with advanced civilizations demands careful preparation. Humanity must establish protocols for first contact that balance scientific curiosity with caution and respect. Such encounters would not only redefine our understanding of life, but also challenge existing belief systems, requiring a flexible and open-minded approach to integrating new knowledge. The multiverse, should it be confirmed, adds an additional layer of complexity to this preparation. Exploring alternate realities, if feasible, will require unprecedented technological, ethical, and philosophical frameworks. Questions about intervention, coexistence, and the rights of beings in other universes will force humanity to expand its understanding of morality and responsibility on a cosmic scale. Finally, humanity must cultivate a sense of cosmic stewardship. As we explore and possibly colonize other planets, moons, or even alternate dimensions, we carry the responsibility to preserve and protect the environments we encounter. The mistakes of Earth deforestation, pollution, and habitat destruction must not be repeated on other worlds. Space exploration offers a chance to demonstrate that humanity can act as a force for preservation and creation, rather than exploitation and destruction. In preparing for a cosmic future, humanity stands at a crossroads. The choices we make now will determine not only our ability to explore the universe, but also the kind of explorers we become. Will we approach the cosmos with humility, curiosity, and a commitment to shared progress? Or will we repeat the errors of history on an interstellar scale? The stars call to us, offering boundless opportunities, but only if we rise to meet them with wisdom and foresight. As we prepare for this journey, we are left with the ultimate question. What will humanity's legacy be in the vast expanse of space and time? Will we become creators of new worlds, guardians of cosmic life, or a fleeting moment in an infinite universe? The answer lies not in the stars but in ourselves. Humanity's legacy in the cosmos. As we cast our gaze toward the stars, we must confront the profound question of legacy. What imprint will humanity leave on the universe? In a cosmos governed by immense scales of space and time, will our existence resonate as a defining chapter, or will it fade into the background noise of eternity? The answer depends on the choices we make as we venture beyond Earth and how we carry forward the values that define us. Our legacy begins with knowledge. The pursuit of understanding the nature of matter, the origins of the universe, the secrets of life is the cornerstone of our civilization. By exploring the cosmos, we add to a growing repository of discoveries that enrich not only ourselves but potentially other civilizations, should they exist. If humanity is to be remembered, it will be for the questions we dared to ask and the truths we uncovered. Another aspect of our legacy is the preservation of Earth itself. As the cradle of life, Earth is unique to us, a beacon of diversity in the vast expanse of space. The responsibility to protect this planet, even as we reach for others, is paramount. A civilization that cannot preserve its home cannot hope to thrive elsewhere. Earth may one day become a symbol, a preserved relic of where humanity began, visited by those who live on distant planets and moons. The arts, culture, and philosophies we create are equally vital. These are the expressions of humanity's soul, capturing our hopes, fears, and dreams. As we spread into the cosmos, what stories will we tell? What music, literature, and art will represent us to the universe? These creations transcend language and time, offering a glimpse of what it means to be human. They are the artifacts of our consciousness, preserving the essence of our existence long after the stars that shine upon us today have faded. Technology, too, will define our cosmic legacy. The tools we build, from spacefaring vessels to artificial intelligence, are extensions of our ingenuity. These innovations could become the seeds of interstellar civilizations, enabling humanity to thrive in environments unimaginable today. But they must be wielded with care, ensuring that the pursuit of progress does not come at the cost of ethics, diversity, or the well-being of future generations. Our interaction with potential extraterrestrial life will leave an indelible mark on our legacy. Whether we encounter microbes on Mars or civilizations among the stars, our approach will speak volumes about who we are. Will we act as explorers driven by respect and curiosity, or will we fall into patterns of exploitation and dominance? The way we engage with life beyond Earth could shape not only our future but also the broader narrative of intelligent life in the universe. Humanity's legacy also lies in our resilience. The challenges we face today, climate change, inequality, and conflict, are trials that will test our capacity to evolve and adapt. The solutions we devise and the unity we foster in overcoming these crises will set the foundation for our cosmic future. The ability to rise above division and short-sightedness is as crucial to our survival as the rockets that carry us into space. In contemplating legacy, we must also consider humility. The universe is vast, and our place within it is small. Yet, it is precisely this smallness that makes our existence extraordinary. Against the backdrop of stars and galaxies, humanity's story is one of consciousness emerging from chaos, of beings capable of pondering their origins and shaping their destiny. Our legacy, then, is not just what we leave behind, but the very act of striving, of reaching for the infinite with finite hands. Ultimately, humanity's legacy will not be written in stone or starlight, but in the ripples we create, ripples of knowledge, connection, and wonder. Whether or not other beings ever find the traces of our civilization, our greatest achievement may be that we dared to dream beyond the boundaries of what we knew, to explore not just the cosmos, but the potential of what we could become. The final question remains: what steps must we take today to ensure that this legacy endures? And how can we inspire the generations to come to carry the torch of exploration, creativity, and responsibility into the vast unknown? Cosmic immortality: humanity's place in the eternal narrative. To secure a legacy that spans the cosmos, humanity must think beyond survival and focus on achieving something far greater: cosmic immortality. This concept does not mean defying death at an individual level, but ensuring that the essence of humanity, our culture, knowledge, creativity, and contributions endures for as long as the universe itself allows. The journey to achieve this immortality is not only a technical and logistical challenge, but also a philosophical one, requiring us to transcend current limitations and embrace our role as participants in the grand cosmic narrative. The foundation of cosmic immortality begins with preserving the story of humanity. As we progress into an era of interstellar exploration and eventual colonization, we must ensure that our knowledge and culture are safeguarded against the ravages of time. This effort involves creating archives so resilient that they can withstand cosmic radiation, planetary upheavals, and even the death of stars. These archives could take many forms: data etched into synthetic diamond, stored in quantum states, or even encoded within the DNA of engineered organisms that could survive in extreme environments. Such archives wouldn't merely preserve humanity's scientific achievements. They would include art, music, literature, and the intangible elements that make us who we are. Imagine a repository drifting through the cosmos, containing the works of Shakespeare, the music of Beethoven, the paintings of Van Gogh, and the thoughts of every great philosopher, messages in a bottle for a universe that may or may not ever find them. In this way, humanity's cultural heritage could become a beacon in the void, a reminder that in one corner of existence, life not only thrived but dreamed. Preservation alone, however, is not enough. To truly achieve cosmic immortality, humanity must adapt and evolve in ways that enable us to thrive in environments far removed from Earth. This means rethinking what it means to be human. Advances in genetic engineering, biohacking, and synthetic biology could allow future generations to modify their bodies to survive extreme conditions, from the thin atmospheres of Mars to the frozen oceans of Europa. The human form, as we know it, might become one of many adaptations, tailored to specific worlds and environments. Equally critical is the development of artificial intelligence and digital consciousness. If biological life proves too fragile for interstellar travel or the harsh realities of distant planets, humanity's essence might persist in the form of digital mind, sentient constructs capable of navigating the stars without the limitations of organic bodies. These digital beings could carry forward human values, creativity, and individuality, creating a hybrid legacy that blends the biological and the artificial. This path raises profound ethical questions. If humanity transforms into a species of genetically enhanced beings or digital minds, will we still be human? What values and principles should guide such transformations? How do we ensure that in the pursuit of immortality, we do not lose the very essence of what makes us unique? These are not obstacles but opportunities for growth, challenges that will push us to redefine identity, community, and the meaning of existence. Another key to cosmic immortality lies in expanding humanity's reach across the universe. Colonizing a single planet or system, while vital for survival, leaves us vulnerable to cosmic catastrophes, supernovae, gamma-ray bursts, or the eventual heat death of our galaxy. True security requires diversification, spreading life to as many worlds as possible. This is the ultimate insurance policy against extinction, ensuring that even if one colony falls, others will persist. Interstellar colonization demands advancements in propulsion and energy systems capable of reaching distant star systems within human lifetimes. Concepts such as antimatter engines, fusion-powered spacecraft, and even the theoretical Alcubierre warp drive hold promise. Additionally, the idea of generational ships, self-sustaining vessels that house entire communities as they journey across the stars, may provide a practical solution for exploring nearby systems like Proxima Centauri or Tau Ceti. Yet, even as we expand outward, the question arises: what will we find? The multiverse concept suggests that our universe is not the only one, and some cosmologists speculate that exploring alternate dimensions or realities might one day become feasible. If so, humanity could become a multiverse-traversing civilization, leaving traces not just across galaxies, but across entire planes of existence. The implications of such exploration defy comprehension. What might we learn from other universes with different laws of physics, histories, and possibilities? How might these discoveries reshape our understanding of life and purpose? In the farthest reaches of time, humanity must prepare for the ultimate challenges posed by the universe's evolution. As the cosmos expands, stars will burn out, galaxies will drift apart, and entropy will increase. In the Big Freeze scenario, the universe becomes a cold, dark expanse where no new energy sources remain. In a Big Rip, the acceleration of dark energy tears apart not just galaxies but the very fabric of spacetime. Even in these apocalyptic futures, humanity's ingenuity might allow us to persist. One speculative solution is the creation of artificial universes, self-contained realms where life can continue to thrive long after the death of our own cosmos. Advanced civilizations might harness energy from black holes, use quantum mechanics to manipulate spacetime, or even engineer conditions that allow for new Big Bangs, seeding fresh universes. If humanity masters such technologies, we could become not just participants in the cosmic story but creators of it. Another possibility lies in transcending the constraints of time itself. Theoretical physics suggests that time may not be linear or even fundamental, but rather an emergent property of the universe. If so, advanced civilizations might learn to manipulate time, creating pockets of existence that persist indefinitely, or even looping back to experience reality anew. These ideas remain speculative, but they highlight the boundless potential of a species willing to embrace the unknown. Amid all these grand visions, the heart of humanity's legacy remains our capacity for meaning. In a universe that may be infinite and indifferent, humanity's pursuit of knowledge, beauty, and connection is an act of defiance against chaos. By reaching for the stars, preserving what we value, and adapting to the cosmos's challenges, we assert that our existence matters, that life, in all its forms, is a force worth preserving and celebrating. What will the cosmos remember of us? Perhaps it will not be the technologies we create or the worlds we colonize, but the simple fact that, for a time, beings existed who marveled at the stars and dreamed of touching them. Humanity's journey to cosmic eternity. The universe's vastness is an unyielding reminder of the challenges we face in carving out a permanent place in its endless expanse. To leave an eternal legacy, humanity must embrace a bold synthesis of technology, philosophy, and adaptability. This is not just a task of survival, but one of transformation, of becoming a species that thrives across the cosmos, capable of enduring even the most hostile environments and catastrophic events. The immediate steps toward such a future are rooted in the advancements of today. Space exploration and the establishment of human presence beyond Earth are not distant dreams, they are realities unfolding before us. Projects like NASA's Artemis program, aiming to return humans to the Moon, and SpaceX's Mars colonization ambitions are the first building blocks of humanity's expansion. But these efforts, while groundbreaking, are merely the beginning. The road to cosmic immortality will demand technologies and strategies that transcend the limits of our current understanding. At the core of this effort lies the challenge of interstellar travel. Reaching even the nearest star systems requires propulsion systems orders of magnitude more advanced than today's rockets. Nuclear fusion propulsion offers a tantalizing possibility, converting the energy released from fusing hydrogen isotopes into powerful, sustained thrust. Theoretically, such engines could achieve speed sufficient to make interstellar journeys feasible within a human lifetime. However, the engineering challenges of safely containing fusion reactions and converting them into efficient propulsion remain formidable. Antimatter engines, though still theoretical, hold even greater potential. When antimatter meets matter, the annihilation releases energy with 100% efficiency, a process far more powerful than chemical or nuclear fusion reactions. A spacecraft powered by antimatter could potentially reach up to 50% of the speed of light, reducing travel times to Proxima Centauri to a few decades. The main obstacle here is not just producing antimatter in sufficient quantities, but also safely storing it in conditions that prevent catastrophic interactions with matter. Beyond these near-term solutions, more speculative concepts like the Alcubierre warp drive offer tantalizing possibilities. By bending space-time itself, a warp drive could allow a spacecraft to effectively ride a bubble of space-time, bypassing the relativistic limitations imposed by traveling through space at conventional speeds. Such a method would not violate Einstein's laws of relativity because the spacecraft would remain stationary within the bubble while spacetime around it moved. Theoretical and practical challenges abound, from the need for exotic negative energy to the construction of spacetime manipulation devices. But the concept underscores humanity's willingness to dream beyond known physics. Even if interstellar travel becomes a reality, humanity must confront the biological, psychological, and social challenges of surviving and thriving in alien environments. Planets outside our solar system, exoplanets, are diverse and often hostile, ranging from scorching, tidally locked worlds to icy giants orbiting dim red dwarfs. To adapt, humanity must consider not only technological solutions like terraforming but also biological ones. Genetic engineering offers a path to resilience. CRISPR and other genome editing technologies have already demonstrated the ability to modify human DNA. In the future, these tools could be used to enhance human tolerance to radiation, enable survival in low oxygen environments, or even allow for photosynthetic skin that provides energy from sunlight. Such modifications would not only improve survival chances but might also enable humans to thrive in environments vastly different from Earth's. However, this raises profound ethical questions. How far should humanity go in altering itself to fit alien worlds? Should the goal be to preserve the human form as we know it, or should we embrace a post-human future where genetic and cybernetic modifications blur the line between human and machine? These are not just scientific challenges but moral ones, forcing humanity to confront the definition of what it means to be human. In the longer term, the concept of digital consciousness offers a radical solution to the challenges of interstellar travel and colonization. If human minds could be uploaded into digital systems, they could transcend the biological limitations of food, oxygen, and physical vulnerability. Digital beings could travel vast distances in suspended animation, residing in virtual environments until they arrive at their destinations. Once there, advanced robotics and nanotechnology could construct physical bodies or habitats for these digital consciousnesses to inhabit. This path, while speculative, aligns with ongoing advancements in artificial intelligence and brain-computer interfaces. Projects like Elon Musk's Neuralink and similar initiatives aim to bridge the gap between human consciousness and digital systems. If these technologies mature, they could allow humanity to persist in forms unbound by biology, spreading our essence across the universe, even in the face of ecological or cosmic catastrophes. As humanity expands its presence in the cosmos, it will inevitably encounter new forms of life, whether microbial organisms beneath the icy crusts of moons like Europa, or intelligent civilizations inhabiting distant star systems. The discovery of extraterrestrial life would represent a profound shift in our understanding of the universe and our place within it. If intelligent civilizations exist, humanity must grapple with how to approach contact, balancing the drive to learn with the need for caution. First contact scenarios raise complex ethical dilemmas. How do we ensure that our actions do not harm or exploit other forms of life? What responsibilities do we have to beings who might be fundamentally different from us in both biology and cognition? And if these civilizations are more advanced than our own, how do we prepare for the possibility that we may be perceived as insignificant or even as a threat? These questions require not just scientific preparation but philosophical introspection, as they challenge our assumptions about morality, value, and the universality of human principles. The multiverse concept adds yet another layer of complexity to humanity's cosmic aspirations. If parallel universes exist, accessible through quantum mechanics or advanced spacetime technologies, the potential for exploration and discovery expands exponentially. In these alternate realities, the laws of physics, the trajectory of evolution, and even the existence of humanity itself could differ. Interacting with such universes would require not just technological innovation, but entirely new frameworks for understanding reality. The ultimate challenge lies in preparing for the farthest reaches of cosmic time. As the universe ages, stars will burn out, galaxies will drift apart, and entropy will increase. In a big freeze scenario, humanity must find ways to generate and store energy in an increasingly hostile environment. Black holes, with their immense gravitational energy, could serve as power sources, harnessed through advanced megastructures like Dyson spheres or Penrose processes. Even more speculative is the idea of creating new universes, engineered realms where life can continue to thrive. This would require an unprecedented mastery of physics, allowing humanity to manipulate the conditions of space-time and initiate new Big Bangs. If successful, humanity could transition from being inhabitants of the cosmos to creators of it, ensuring that life continues indefinitely, even as the current universe fades into darkness. As we contemplate these far-reaching possibilities, one truth becomes clear: humanity's legacy will not be defined by the tools we build or the worlds we colonize, but the values we carry forward. The pursuit of knowledge, the preservation of life, and the cultivation of beauty and meaning are the hallmarks of a species worthy of immortality. These are the ideals that must guide us as we venture into the cosmos, ensuring that in the infinite vastness of space, humanity's light continues to shine. The infinite horizon, humanity's expansion into eternity. The vastness of the universe offers both a challenge and an opportunity for humanity's ultimate survival and relevance. With trillions of galaxies, each containing billions of stars and untold numbers of planets, the possibilities for exploration and habitation are endless. However, this abundance also requires strategic thinking, technological innovation, and philosophical introspection to ensure that humanity's expansion into eternity is not only sustainable but meaningful. As we set our sights on becoming a multi-planetary and eventually multi-stellar civilization, the challenges of scaling our presence across such immense distances become clear. The nearest star systems are separated from us by years of travel at the speed of light. The further we go, the greater the need for self-sustaining technologies that allow entire ecosystems to function independently of Earth. Interstellar megastructures and generation ships. One of the first practical steps toward interstellar colonization may involve the construction of massive, self-contained habitats known as generation ships. These vessels, capable of supporting human life for centuries, would be designed as miniature ecosystems, complete with recycling systems for air, water, and nutrients, as well as artificial gravity to maintain human health. Aboard such ships, entire societies could evolve, carrying human culture, knowledge, and traditions to new star systems. Generation ships would also require revolutionary advancements in energy efficiency and propulsion. Nuclear fusion reactors could provide the immense energy needed for long-term voyages, powering not only the ship's propulsion systems, but also its life support and agricultural modules. The challenge lies in making such systems durable and fail-safe for journeys spanning centuries or millennia. As humanity grows more ambitious, the concept of interstellar megastructures such as Dyson swarms or stellar engines becomes increasingly relevant. A Dyson swarm, a collection of satellites orbiting a star, could harness massive amounts of energy to power interstellar missions or support colonies on distant planets. Stellar engines, on the other hand, could manipulate the motion of stars, guiding entire solar systems through the galaxy over millions of years. These megastructures would represent humanity's mastery over its environment on a cosmic scale. Colonizing exoplanets and adaptation to alien worlds. The discovery of exoplanets and habitable zones around distant stars has reignited hopes of finding Earth-like worlds. These planets, with conditions similar to our own, may provide the best opportunities for colonization. However, even the most Earth-like planets will require adaptation. Their atmospheres, temperatures, and gravitational forces will likely differ from what humans are accustomed to. Terraforming, the process of transforming a planet's environment to make it habitable, offers one solution. This could involve releasing greenhouse gases to warm a planet, introducing microbial life to generate oxygen, or constructing massive shields to protect against harmful radiation. While promising, terraforming is a time-intensive process, likely taking centuries or millennia to yield results. Alternatively, humanity might adapt itself to alien worlds rather than altering those worlds to suit human needs. Genetic engineering could enhance human resilience to radiation, modify metabolism to survive on limited resources, or even allow humans to breathe alien atmospheres. These adaptations would fundamentally alter what it means to be human, creating a species capable of thriving in environments far removed from Earth. Beyond biology, the rise of digital and hybrid lifeforms. As humanity pushes further into the cosmos, the limits of biological life become increasingly apparent. Space is inherently hostile to organic beings. Radiation, microgravity, and the lack of essential resources make prolonged survival challenging. To overcome these limitations, humanity may turn to digital consciousness and hybrid lifeforms as the next stage of evolution. The idea of uploading human minds into digital systems has long been a staple of speculative fiction, but advancements in neuroscience and artificial intelligence bring it closer to reality. Digital consciousness would allow humans to exist as software, capable of inhabiting virtual environments or interfacing directly with machines. Freed from the constraints of biology, digital beings could travel vast distances as data, requiring only minimal energy and resources. Hybrid lifeforms, combining biological and mechanical components, offer another path forward. By integrating advanced prosthetics, neural interfaces, and synthetic organs, humans could enhance their physical and cognitive abilities, becoming more adaptable to extreme conditions. These transhuman advancements would not only extend lifespans but also enable humans to interact with their environments in entirely new ways. The ethical challenges of cosmic expansion. With great power comes great responsibility. Humanity's expansion into the cosmos raises profound ethical questions about how we interact with other worlds, other species, and even other forms of life we might create. The mistakes of the past, colonial exploitation, environmental destruction, and disregard for indigenous cultures, must not be repeated on a cosmic scale. The discovery of microbial life on planets like Mars or Europa would force humanity to confront the question of planetary preservation. Should we prioritize the study and protection of alien ecosystems, or should we prioritize human survival and expansion? If intelligent extraterrestrial civilizations exist, how do we engage with them in a way that respects their autonomy and avoids conflict? The creation of artificial life, whether digital consciousness or advanced AI, also raises questions of rights and responsibilities. If these beings possess self-awareness, should they have the same rights as biological humans? How do we ensure that their development aligns with ethical principles, avoiding scenarios where they are exploited or used as tools for conquest? Humanity's role as cosmic creators. The ultimate step in humanity's journey to cosmic eternity may involve not just exploring and colonizing the universe, but actively shaping it. Advances in physics and cosmology suggest that one day we may be able to manipulate space-time itself, creating new worlds, galaxies, or even universes. This would elevate humanity from participants in the cosmos to creators of it. Such acts would carry immense moral weight. What responsibilities do we have to the beings that might inhabit these created realms? How do we ensure that our actions as creators are guided by compassion, wisdom, and respect for life in all its forms? These questions challenge humanity to evolve not just technologically but ethically, becoming stewards of existence itself. A legacy of meaning. In the face of the infinite, the question of meaning becomes paramount. Why should humanity strive for cosmic immortality? What makes our existence valuable in a universe that may be indifferent to our presence? The answers lie not in the cosmos but in ourselves. Humanity's legacy will be defined by the values we uphold, the knowledge we preserve, and the connections we forge. Whether we remain a single-species civilization or spread across the stars, our greatest achievement will be the act of striving, of reaching beyond what we know and daring to imagine what could be. In the distant future, when the light of the last stars begins to fade and the universe approaches its end, humanity's presence may persist as a testament to the resilience of life and the boundless potential of consciousness. Whether as biological beings, digital entities, or creators of new realities, we will leave a mark on existence, a legacy that echoes through eternity. This is the challenge and the promise of the infinite horizon, to ensure that humanity's light, however small, continues to shine in the vast darkness of the cosmos. The boundless vision of humanity's cosmic destiny. Humanity's destiny is as much a matter of imagination as it is of action. The universe, with its endless expanse and infinite mysteries, demands not just the will to explore but the creativity to envision what lies beyond the limits of our current knowledge. To embrace this destiny is to acknowledge that the path forward requires a complete redefinition of what it means to exist, adapt, and thrive within the cosmos. The scale of this challenge is staggering. The Milky Way alone spans 100,000 light-years, home to hundreds of billions of stars and potentially trillions of planets. Beyond our galaxy, the universe contains at least 2 trillion galaxies, each representing a wellspring of untapped potential for exploration, knowledge, and colonization. Yet, this vastness is not a deterrent, it is an invitation. The impossibility of conquering the universe in its entirety does not diminish the importance of striving to extend humanity's reach. Every step forward is a triumph, every new world a chapter in the story of life expanding its boundaries. The first steps in humanity's cosmic journey begin within our solar system. Mars, often called the next frontier, represents a vital proving ground. The red planet challenges us to develop technologies that will ensure survival in a hostile environment. Its thin atmosphere, frigid temperatures, and barren landscape require solutions that blend innovation with sustainability. Habitats must be designed to shield inhabitants from cosmic radiation, recycle water and air efficiently, and generate food through advanced hydroponics or even Martian soil manipulation. These efforts will not only lay the groundwork for colonization, but also teach us how to live off-world sustainably, skills that will be crucial for more distant endeavors. Beyond Mars, the icy moons of Jupiter and Saturn, Europa, Enceladus, and Titan offer compelling opportunities. Beneath Europa's frozen crust lies a vast ocean of liquid water, kept warm by tidal forces from Jupiter. Enceladus, too, hides subsurface oceans, while Titan's thick atmosphere and hydrocarbon lakes present an entirely different set of conditions ripe for exploration. Establishing outposts on these moons will require new engineering paradigms. Autonomous underwater vehicles may probe Europa's oceans, searching for signs of life, while floating habitats could drift above Titan's methane seas. Each success here brings us closer to understanding the versatility of life and the adaptability of human ingenuity. However, the solar system is but a stepping stone. True cosmic expansion necessitates interstellar travel, a feat that remains far beyond our current capabilities. The physical challenges are immense. The vast distances, the scarcity of energy, and the need for self-sustaining ecosystems capable of enduring centuries-long voyages. Yet, history is a testament to humanity's ability to overcome seemingly insurmountable obstacles. The development of faster-than-light travel, though speculative, embodies humanity's unyielding determination to defy natural limits. Concepts like the Alcubierre warp drive, which manipulates spacetime to allow a ship to traverse vast distances without violating relativity, offer a tantalizing glimpse of what might one day be possible. Even without such breakthroughs, advances in propulsion systems, such as nuclear fusion or antimatter engines, could make travel to nearby stars feasible within a few generations. Interstellar travel is not merely a matter of propulsion. It demands the creation of habitats that can sustain human life indefinitely. These generation ships would become microcosms of humanity, carrying the seeds of Earth's civilizations to distant star systems. On board, future generations would live, work, and evolve, never knowing Earth firsthand yet preserving its culture, history, and values. Such ships would need to balance technological autonomy with social harmony, ensuring that they remain functional and cohesive over centuries. Upon arrival at new star systems, the challenges multiply. Planets that orbit in the habitable zones of their stars may still require significant adaptation. Gravity, atmospheric composition, and local resources will vary dramatically, and colonists must be prepared to modify either the environment or themselves to survive. Terraforming, while ambitious, could transform barren worlds into lush habitats over millennia. Alternatively, human genetic engineering might create new versions of humanity, adapt to specific planetary conditions, beings who can breathe alien atmospheres, tolerate extreme temperatures, or survive without sunlight. As humanity spreads through the galaxy, its identity will inevitably change. Cultural evolution will diverge as colonies adapt to their unique environments. Over time, isolated populations may develop distinct languages, traditions, and even physical characteristics. What begins as a unified species may fragment into a diversity of human descendants, each uniquely adapted to their corner of the cosmos. This fragmentation is not a loss, but a celebration of humanity's capacity for transformation and creativity. Parallel to these physical expansions, humanity may also explore existence in forms beyond biology. Advances in artificial intelligence and neuroscience suggest the possibility of uploading consciousness into digital systems, creating sentient beings free from the limitations of organic matter. These digital entities could travel vast distances as data, reassembling themselves upon arrival or existing entirely within virtual constructs. This form of existence could coexist alongside biological humanity, expanding the definition of life and intelligence. The multiverse adds another dimension to this vision. If alternate realities exist, they represent an infinite frontier not bound by the physical laws of our own universe. Exploring these realms, should it become possible, would redefine the scope of human potential. The multiverse is not merely a collection of possibilities, it is a challenge to our understanding of reality itself. In encountering universes where the constants of nature differ, where life takes on forms unimaginable, humanity would confront the deepest questions about existence and our place within it. The ultimate fate of humanity lies not just in its ability to expand but in its capacity to endure. The universe's long-term trajectory, a gradual cooling and dimming as stars burn out and galaxies drift apart, demands solutions that are as visionary as they are audacious. Harnessing the energy of black holes, creating artificial stars, or even engineering new universes through advanced physics are not just speculative ideas, they are necessities for a species intent on transcending its limitations. In this far future, humanity may no longer resemble its present form. Whether as biological beings, digital consciousness, or something entirely beyond our current understanding, the essence of what we are, our curiosity, creativity, and drive must persist. This essence is the true legacy of humanity, a testament to life's ability to find meaning even in the face of cosmic indifference. The journey into the cosmos is not just a physical endeavor but a philosophical one. It challenges humanity to rise above division, short-sightedness, and self-doubt, embracing a vision that is as grand as the universe itself. Each step forward, whether it is a colony on Mars or a message sent to another galaxy, is an affirmation of life's resilience and its boundless potential. When the stars themselves fade and the universe enters its final stages, humanity's story may still continue. Whether we exist as creators of new realities, travelers of the multiverse, or simply as a memory encoded in the fabric of space-time, our presence will have shaped the cosmos in ways both profound and lasting. This is the legacy we strive for, not just to survive, but to illuminate the infinite with the light of our existence. Eternal resonance, humanity's quest for immortality in the cosmos. To approach the idea of humanity's eternal resonance within the cosmos, we must think not only about survival but about thriving, evolving, and leaving a profound mark on the universal stage. The infinite expanse of the universe, and perhaps the multiverse, offers us boundless opportunities to expand our presence and define our legacy. Achieving this requires more than technology. It demands a new way of thinking about existence, purpose, and responsibility. Humanity's immediate steps into the cosmos will be the foundation of this long-term vision. Colonizing Mars, mining asteroids, and building self-sustaining lunar bases are critical milestones. These projects serve not only as technological achievements, but as proof that humanity can adapt to environments far removed from Earth's protective cradle. The lessons learned from creating closed-loop ecosystems, generating energy in hostile conditions, and cultivating food in barren soils will prepare us for more distant journeys. Yet, as we push outward, the complexity of our challenges will increase exponentially. Interstellar travel, while conceptually thrilling, confronts us with distances and timescales that strain our comprehension. The nearest star system, Alpha Centauri, is over 4 light-years away, a distance that would take tens of thousands of years to traverse with current technology. Overcoming this limitation demands a revolution in propulsion and energy. Fusion propulsion, capable of harnessing the energy of stars, represents the most plausible near-term solution. Fusion engines could provide continuous thrust over long periods, reaching speeds that significantly reduce travel times to nearby stars. Developing such engines requires breakthroughs in magnetic confinement, plasma stability, and energy conversion efficiency. These challenges, while daunting, are surmountable with sustained investment and ingenuity. For greater speeds, antimatter propulsion becomes a tantalizing possibility. Antimatter reactions release energy orders of magnitude greater than any chemical or nuclear process, making them ideal for interstellar journeys. However, the production and containment of antimatter remain significant hurdles. Even a gram of antimatter requires immense energy to produce, and storing it safely requires advanced magnetic or electrostatic traps. Progress in this field could open the door to travel at a significant fraction of the speed of light. Theoretical technologies, such as warp drives and wormholes, push the boundaries of physics. A warp drive, as described by physicist Miguel Alcubierre, involves contracting spacetime ahead of a spacecraft and expanding it behind, allowing faster-than-light travel without violating relativity. Similarly, wormholes, shortcuts through spacetime, could enable instantaneous travel across vast distances. While these concepts are speculative, they highlight humanity's capacity to imagine and strive for solutions beyond current limitations. Even with advanced propulsion, interstellar travel requires a new approach to habitation. Generation ships, massive self-contained ecosystems, offer a solution for journeys spanning centuries or millennia. These ships would not only sustain human life but also support entire societies, with their own economies, governance systems, and cultural practices. Designing such vessels involves integrating sustainable life support systems, radiation shielding, and psychological support for long-term isolation. Artificial intelligence will play a pivotal role in managing these complexities. Autonomous AI systems could oversee ship functions, make real-time decisions, and ensure the well-being of passengers. Beyond their practical applications, AI entities might also serve as companions, educators, and mediators, fostering social cohesion within the confines of a generation ship. Upon reaching distant star systems, humanity will face the challenge of establishing footholds on alien worlds. Exoplanets in the habitable zones of their stars are the most promising targets, but even these will differ vastly from Earth. Their atmospheres may be toxic, their climates extreme, and their ecosystems alien. Terraforming, a process that modifies a planet's environment to resemble Earth's, offers one solution. This might involve introducing greenhouse gases to warm the surface, seeding microbial life to generate oxygen, or constructing planetary-scale shields to regulate temperature and radiation. Terraforming, however, is a long and resource-intensive process. In many cases, adapting humans to the environment may be more practical than altering the environment itself. Genetic engineering could enable humans to thrive in low-gravity conditions, metabolize different atmospheres, or withstand higher levels of radiation. These adaptations, while transformative, raise ethical questions about the boundaries of humanity and the preservation of our identity. Parallel to these efforts, humanity must consider the potential for post-biological existence. Advances in brain-computer interfaces and neural emulation may one day allow human consciousness to transcend its biological substrate. Digital minds capable of inhabiting virtual realities or interfacing with robotic bodies would be far better suited for the rigors of interstellar travel and colonization. These beings could operate without the need for food, air, or sleep, dramatically reducing the logistical challenges of space exploration. This path, while practical, forces us to confront profound philosophical questions. If humanity transitions to a digital or hybrid form, what happens to the essence of what makes us human? Will our values, emotions, and individuality persist in these new forms? Or will we become something entirely new, a continuation of humanity, but not humanity as we know it? As we expand into the galaxy, our interaction with extraterrestrial life will define our legacy. Whether we encounter microbial life on Mars, complex organisms on Europa, or intelligent civilizations around distant stars, our approach will reflect our values and aspirations. Will we act as explorers driven by curiosity and respect, or will we repeat the mistakes of colonial exploitation? These encounters will challenge us to rethink our place in the cosmos and our responsibility to other forms of life. The multiverse, if it exists, adds yet another dimension to humanity's journey. Parallel universes, each with its own physical laws and histories, represent an infinite frontier. Exploring these realms, should it become possible, would require technologies and philosophies that transcend anything we currently possess. What might we learn from universes where life evolved under different conditions, or where intelligence took forms we cannot yet imagine? These encounters would redefine not only our understanding of reality, but also our sense of identity. Ultimately, humanity's long-term survival hinges on our ability to adapt to the universe's changing conditions. The cosmos is not static, stars burn out, galaxies collide, and the very fabric of space-time evolves. In the distant future, when the last stars fade and the universe approaches its end, humanity must find ways to endure. This might involve harnessing the energy of black holes, creating artificial stars, or even engineering new universes through advanced physics. This vision is not mere fantasy. It represents the logical extension of humanity's drive to explore, innovate, and survive. By embracing this vision, we affirm our commitment to life's resilience and its capacity for boundless growth. The universe may be vast and indifferent, but within it, humanity can carve out a legacy that resonates for eternity. Our story is just beginning. As we step into the cosmos, let us carry forward the values that define us: curiosity, creativity, and a deep respect for the interconnectedness of all things. In doing so, we ensure that humanity's light will continue to shine, not just on Earth, but across the infinite expanse of existence. The infinite tapestry of humanity's cosmic ambition. To understand the scope of humanity's potential, we must imagine a timeline that stretches beyond the lifespan of stars, beyond the lifespan of galaxies, and perhaps beyond the lifespan of the universe itself. The human journey is not limited to the confines of Earth, our solar system, or even our own galaxy. It is a story of resilience, innovation, and the relentless pursuit of meaning in a cosmos that offers endless opportunities and challenges. As we venture deeper into the universe, each step forward demands a synthesis of creativity and practicality. The planets of our solar system provide the perfect starting point, offering environments where humanity can test its ability to survive and thrive away from Earth. Mars is the first major milestone, but the lessons we learn there will lay the groundwork for more ambitious undertakings, such as colonizing the icy moons of Jupiter and Saturn or constructing vast habitats in orbit around gas giants. Space habitats themselves represent a critical step in humanity's expansion. Unlike planetary colonization, space habitats can be built in a variety of locations. From the stable Lagrange points of our solar system to the asteroid belts rich in minerals and resources. These habitats, designed as closed-loop ecosystems, will be engineered to support human life indefinitely, with systems that recycle air, water, and nutrients with near-perfect efficiency. Their modular nature will allow them to grow over time, transforming into orbital cities or even interconnected networks of habitats spanning entire star systems. The development of these habitats will coincide with the rise of asteroid mining, a crucial industry for the future of space exploration. The asteroid belt between Mars and Jupiter contains trillions of dollars worth of resources, including rare earth metals, water ice, and materials essential for constructing spacecraft and habitats. Mining these asteroids will not only reduce humanity's reliance on Earth's finite resources, but also enable the construction of megastructures that could support billions of people in space. One such megastructure, the Dyson Swarm, is a theoretical construct designed to capture nearly all of a star's energy output. By surrounding a star with a network of solar collecting satellites, humanity could harness energy on a scale unimaginable today. This energy could power interstellar spacecraft, sustain vast colonies, or even fuel experiments in advanced physics aimed at manipulating spacetime itself. The construction of a Dyson Swarm would represent humanity's transition from a planetary species to a stellar one, marking the beginning of our influence on a galactic scale. The leap to interstellar travel will be one of the most significant challenges humanity has ever faced. While current propulsion technologies are sufficient for exploration within our solar system, they are woefully inadequate for the vast distances between stars. Even with optimistic advancements in fusion or antimatter propulsion, the journey to Proxima Centauri, our nearest stellar neighbor, would take decades or centuries. For more distant stars, new paradigms are needed. Theoretical concepts like the Alcubierre warp drive offer tantalizing possibilities. By compressing spacetime in front of a spacecraft and expanding it behind, a warp drive could theoretically allow faster-than-light travel without violating the laws of relativity. Such technology would require exotic matter with negative energy density, a material that has not yet been discovered or created. However, the pursuit of such breakthroughs could unlock new realms of physics, reshaping our understanding of the universe and our place within it. In parallel with propulsion advancements, humanity must develop methods for preserving life during long-duration missions. Generation ships, self-sustaining vessels designed to support human life for centuries, offer a practical solution. These ships would function as microcosms of Earth, complete with ecosystems, industries, and social structures. Over time, they would evolve into independent societies, carrying the torch of humanity to distant star systems. Upon reaching new worlds, the process of colonization begins anew. Exoplanets and the habitable zones of their stars offer the most promising opportunities, but even these worlds will require adaptation. Terraforming, though ambitious, may be the only way to create Earth-like conditions on barren planets. This process could take millennia, involving the release of greenhouse gases to warm the planet, the introduction of microorganisms to generate oxygen, and the construction of vast infrastructure to regulate climate and atmosphere. For worlds where terraforming is not feasible, humanity must consider alternative strategies. Genetic engineering offers a powerful tool for adapting humans to alien environments. By modifying our DNA, we could develop traits that allow us to survive in extreme conditions, from high radiation environments to low gravity worlds. Such adaptations would represent a profound shift in what it means to be human, creating a species capable of thriving in environments previously deemed uninhabitable. As humanity spreads across the stars, our understanding of life will inevitably expand. The discovery of extraterrestrial life, whether microbial or intelligent, would be a watershed moment in history. It would force us to confront questions about the universality of life's principles, the ethical implications of contact, and the possibility of coexistence. Intelligent civilizations, if they exist, might have technologies, philosophies, and cultures far beyond our own, offering insights that could reshape our trajectory as a species. The multiverse, if proven real, represents the ultimate frontier. The idea that our universe is one of many, each with its own physical laws and histories, challenges the very foundation of our understanding of existence. Exploring these alternate realities, if technologically feasible, would open infinite possibilities for discovery. What might we learn from universes where the constants of nature differ, or where life evolved under entirely different conditions? The answers could redefine not only our place in the cosmos, but the nature of reality itself. In the distant future, as the universe ages, humanity must prepare for the ultimate challenges of survival. Stars will burn out, galaxies will drift apart, and entropy will increase, leading to a cold and desolate cosmos. To endure, humanity must master the manipulation of energy and matter on an unprecedented scale. Harnessing the energy of black holes, constructing artificial stars, or even engineering new universes through advanced physics could ensure that life persists even as the universe approaches its end. The pursuit of cosmic immortality is not without its risks. The technologies required to manipulate space-time, create artificial life, or explore the multiverse carry inherent dangers. Missteps could lead to existential threats, from rogue AI to unintended consequences of advanced physics experiments. Navigating these risks requires a commitment to ethical principles, global cooperation, and a long-term perspective that prioritizes the well-being of all life. Ultimately, humanity's legacy will be defined not by the technologies we create or the worlds we colonize, but by the values we uphold. Our journey into the cosmos is an opportunity to demonstrate the best of what it means to be human: curiosity, creativity, compassion, and a deep respect for the interconnectedness of all things. By carrying these values into the stars, we ensure that our legacy is one of inspiration and hope, not exploitation or destruction. The cosmos may be vast and indifferent, but within it, humanity has the potential to create meaning. Each step we take, whether it is building a habitat on Mars, sending a probe to another galaxy, or encoding our culture into the fabric of space-time, is an affirmation of life's resilience and its capacity to dream beyond boundaries. The infinite horizon is not just a challenge, it is a promise, a reminder that within the vastness of existence there is always more to discover, create, and celebrate. The Symphony of Eternity, humanity's infinite odyssey. To fully appreciate humanity's potential in the cosmos, we must embrace a vision as grand and boundless as the universe itself. The universe is a canvas of unimaginable scale, and humanity, a fledgling species, stands poised to become its most intricate artist. This journey will not only demand technological ingenuity, but also a transformation of our understanding of life, morality, and purpose. As humanity moves beyond the relative safety of Earth, we enter a domain where survival is no longer a given. Every step forward will test our ability to adapt, innovate, and collaborate. In this light, even the smallest achievements, establishing a sustainable colony on the Moon, mining the asteroid belt for resources, or terraforming the surface of Mars, become milestones in a larger narrative. Each success builds the foundation for the ultimate goal, ensuring that humanity's influence and essence endure for billions, or even trillions of years. Mars, our closest candidate for colonization, symbolizes the dawn of interplanetary living. While its barren landscape and thin atmosphere offer challenges, they are surmountable. Early habitats will rely on advanced technologies, including pressurized living spaces, radiation shields, and renewable energy systems powered by solar arrays or nuclear reactors. Over time, humanity's presence will evolve from a series of isolated outposts into interconnected settlements capable of sustaining millions. Terraforming Mars represents the next logical step. By releasing carbon dioxide trapped in its polar ice caps and subsurface, we could thicken the atmosphere, creating a greenhouse effect to raise surface temperatures. Introducing engineered microorganisms could further enrich the atmosphere with oxygen, while vast networks of mirrors or orbital reflectors might direct sunlight to accelerate warming. Such efforts will span centuries, but the results would transform Mars into a second Earth, capable of supporting diverse ecosystems. Beyond Mars, the moons of the gas giants offer the promise of exploration and habitation. Europa, with its subsurface ocean, and Titan, with its thick atmosphere and hydrocarbon lakes, present environments ripe for scientific discovery and human ingenuity. Submarines capable of withstanding extreme pressures could probe Europa's oceans, while floating cities might drift above Titan's methane seas. These endeavors will require unprecedented advancements in materials science, robotics, and energy systems, but their rewards could redefine our understanding of life's adaptability. However, the solar system is just the beginning. The real challenge lies in crossing the interstellar void, where the distances dwarf even our most ambitious achievements. The nearest star, Proxima Centauri, is 4.24 light-years away, a journey of over 40 trillion kilometers. At current spacecraft speeds, this distance is insurmountable, requiring tens of thousands of years to traverse. To overcome this, humanity must develop propulsion systems that operate on principles entirely different from conventional rocketry. Nuclear fusion propulsion is one of the most promising avenues. Fusion reactors could generate immense amounts of energy by fusing hydrogen isotopes, providing continuous thrust over extended periods. Such technology would enable spacecraft to reach speeds far greater than anything achievable today, cutting interstellar travel times from millennia to mere centuries. Fusion's byproducts, helium and energy, are clean and efficient, making it ideal for long-term missions. Antimatter propulsion represents an even more ambitious possibility. When matter and antimatter collide, they annihilate each other, releasing energy with 100% efficiency. A spacecraft powered by antimatter could reach speeds approaching 50% of the speed of light, making journeys to nearby star systems feasible within human lifetimes. However, producing and storing antimatter remains a significant hurdle, as even a gram of antimatter requires vast amounts of energy to create. Theoretical propulsion systems, such as the Alcubierre warp drive, stretch the imagination further. By contracting spacetime in front of a spacecraft and expanding it behind, a warp drive could allow faster-than-light travel without violating Einstein's theory of relativity. Though this concept requires exotic matter with negative energy density, a material not yet proven to exist, it exemplifies humanity's capacity to dream beyond the constraints of current science. Once we achieve interstellar travel, the focus will shift to establishing footholds on distant planets. Exoplanets orbiting in the habitable zones of their stars are prime targets, offering conditions that may support liquid water and potentially life. These worlds, while promising, will differ vastly from Earth. Their atmospheres may be toxic, their climates extreme, and their ecosystems entirely alien. Terraforming will again play a pivotal role. On some worlds, we might use orbital mirrors to reflect sunlight, warming frozen landscapes. On others, we could release greenhouse gases to trap heat or deploy vast networks of genetically engineered plants to produce oxygen. Each planet will present unique challenges, requiring tailored solutions that blend biology, engineering, and environmental science. For planets where terraforming is not feasible, humanity must adapt to the environment rather than altering it. Genetic engineering could allow humans to withstand high radiation levels, metabolize alien nutrients, or survive in low-gravity conditions. Such adaptations may lead to the emergence of new human subspecies, each uniquely suited to its planetary home. Over millennia, these divergent populations could evolve into entirely new forms of intelligent life, diversifying the human lineage across the stars. As humanity spreads, we will inevitably encounter the question of extraterrestrial life. The discovery of microbial life on Mars or Europa would revolutionize biology, proving that life is not unique to Earth. Intelligent civilizations, if they exist, would challenge us to rethink our place in the cosmos. How we approach these encounters will define our legacy. Will we act as explorers and collaborators? Or will we repeat the mistakes of colonial exploitation? Respect, caution, and open-mindedness must guide our actions. The multiverse adds an even greater dimension to humanity's journey. If alternate realities exist, they offer infinite opportunities for exploration and discovery. These universes, governed by different physical laws or histories, could provide insights into questions that have long eluded us. What might we learn from a universe where time flows backward, or where gravity is repulsive rather than attractive? The possibilities are as boundless as the multiverse itself. As we venture into these new frontiers, humanity must also prepare for the distant future of the universe. Stars will eventually exhaust their fuel, galaxies will drift apart, and the universe will cool as entropy increases. In this far-off era, humanity's survival will depend on mastering energy sources beyond anything we currently understand. Black holes, with their immense gravitational energy, could serve as power sources, harnessed through advanced technologies like Dyson spheres or Penrose processes. In the ultimate scenario, humanity might create new universes, engineered realms where life can continue indefinitely. This would require manipulating the very fabric of space-time, initiating new Big Bangs to seed fresh realities. If successful, humanity would transition from being inhabitants of the cosmos to its creators, ensuring that life endures even as the current universe fades into darkness. The journey toward cosmic immortality is not just a scientific endeavor, it is a moral and philosophical one. It challenges us to confront questions about identity, purpose, and responsibility. As we transcend the boundaries of Earth and biology, what will remain of our humanity? How do we ensure that our actions reflect not just survival but the values that define us: curiosity, creativity, and compassion? In the face of an indifferent universe, humanity has the opportunity to create meaning. Each step into the cosmos, whether it is establishing a colony on Mars, sending a message to another galaxy, or exploring the multiverse, is an affirmation of life's resilience and its capacity to dream. The stars do not need us, but we need them. They are the canvas on which we paint our legacy, the infinite horizon that calls us to become more than we are. When the last stars fade and the universe grows cold, humanity's story may still continue. Whether as biological beings, digital consciousness, or creators of new realities, we will have proven that life is not bound by its origins. It is a force of endless potential, capable of reaching across the void and leaving a mark that resonates for eternity. This is the symphony of eternity, a melody composed not of survival alone, but of exploration, growth, and the unyielding belief that the cosmos is not just a place we inhabit but a destiny we shape. The infinite horizon is ours to embrace, not as conquerors, but as stewards of a legacy that transcends time and space. The eternal legacy, humanity's cosmic evolution. The journey of humanity into the cosmos is a story not merely of exploration but of transformation. As we venture farther from Earth, our very essence, biological, cultural, and intellectual, will evolve to meet the challenges of the vast and diverse environments we encounter. This evolution will not only determine our survival, but will define the legacy we leave behind, a legacy woven into the infinite tapestry of existence. The initial phases of humanity's cosmic journey are already underway. Lunar bases and Martian colonies are within reach, serving as critical testbeds for the technologies and strategies required for deeper space exploration. These early settlements will be built to withstand the rigors of space, extreme temperatures, relentless radiation, and the psychological toll of isolation. They will rely on advanced systems for water recycling, air purification, and sustainable food production. Over time, these outposts will grow into thriving habitats, demonstrating humanity's ability to adapt to environments vastly different from Earth's. From these first steps, humanity will expand outward, constructing orbital habitats and mining the wealth of the asteroid belt. Asteroids, with their abundant supplies of metals like nickel, iron, and platinum, as well as water ice, will provide the raw materials needed to support burgeoning space industries. These industries will, in turn, enable the construction of megastructures such as orbital cities, solar power satellites, and interplanetary transport systems. Such advancements will mark the transition from a single-planet civilization to a spacefaring species. As humanity becomes a spacefaring species, the focus will shift from merely surviving to thriving. Space habitats will evolve into fully self-sustaining ecosystems, supporting millions of inhabitants. These habitats may take the form of O'Neill cylinders, massive rotating structures that provide artificial gravity and house entire cities, or Bernal spheres, enclosed environments capable of supporting complex ecosystems. Over time, these habitats will become centers of innovation, culture, and governance, each a microcosm of humanity's ingenuity and diversity. The leap to interstellar travel will mark a new epoch in humanity's history. To achieve this leap, we must develop propulsion systems capable of traversing the vast distances between stars. While nuclear fusion and antimatter engines offer promising paths, their development will require significant advancements in physics and engineering. Theoretical technologies, such as the Alcubierre warp drive or wormhole travel, push the boundaries of what is currently possible, but represent the kind of ambition necessary for humanity's ultimate goals. Even with advanced propulsion, interstellar travel poses immense challenges. The sheer distances involved necessitate spacecraft capable of supporting life for centuries or even millennia. These generation ships would function as isolated societies, carrying the seeds of humanity to distant star systems. Within these vessels, generations of humans would live, work, and evolve, creating new cultures and traditions that reflect their unique circumstances. Upon reaching new star systems, humanity will face the challenge of colonization. Exoplanets and the habitable zones of their stars offer the most promising opportunities, but even these worlds will require adaptation. Terraforming, though ambitious, may be the only way to create Earth-like conditions on barren planets. This process could take millennia, involving a combination of advanced technologies and biological ingenuity. Terraforming might include deploying orbital mirrors to reflect sunlight, warming frozen landscapes, or introducing genetically engineered microorganisms to produce oxygen. Such efforts would transform these worlds into habitable environments, paving the way for permanent human settlement. For planets where terraforming is not feasible, humanity must adapt to the environment rather than altering it. Genetic engineering could enable humans to withstand high radiation levels, metabolize alien nutrients, or survive in low-gravity conditions. As humanity spreads across the stars, our understanding of life will inevitably expand. The discovery of extraterrestrial life, whether microbial or intelligent, would revolutionize our understanding of biology and the universality of life's principles. Intelligent civilizations, if they exist, would challenge us to rethink our place in the cosmos and the ethical implications of contact. How we approach these encounters will define our legacy. Will we act as explorers and collaborators, or will we repeat the mistakes of colonial exploitation? The possibility of intelligent extraterrestrial civilizations also raises profound questions about the nature of consciousness and intelligence. If we encounter beings vastly different from ourselves, with modes of thought and communication we cannot comprehend, how will we bridge the gap? The development of advanced AI and neural interfaces may provide tools for understanding and interacting with these civilizations, fostering a spirit of cooperation and mutual respect. Beyond the physical expansion into space lies the potential for humanity to transcend its biological limitations. Advances in neuroscience and artificial intelligence suggest that human consciousness might one day be digitized, allowing individuals to exist as digital beings unbound by the constraints of biology. These digital entities could inhabit virtual environments, travel as data, or integrate with robotic systems, enabling humanity to explore the cosmos in entirely new ways. The digitization of consciousness raises profound ethical and philosophical questions. What does it mean to be human in a post-biological world? Can a digital mind retain the essence of humanity, or will it become something entirely new? These questions challenge us to reconsider the nature of identity, individuality, and the value of life. As humanity explores these new frontiers, the multiverse offers an even greater challenge. If parallel universes exist, each with its own physical laws and histories, they represent an infinite frontier for discovery. Exploring these realms would require technologies and philosophies that transcend anything we currently possess. What might we learn from universes where time flows backward, or where gravity behaves in ways we cannot imagine? The possibilities are as boundless as the multiverse itself. In the distant future, humanity must prepare for the ultimate challenges of survival. Stars will eventually exhaust their fuel, galaxies will drift apart, and the universe will cool as entropy increases. To endure, humanity must master energy sources beyond anything we currently understand. Black holes, with their immense gravitational energy, could serve as power sources, harnessed through advanced technologies like Dyson spheres or Penrose processes. In the ultimate scenario, humanity might create new universes, engineered realms where life can continue indefinitely. This would require manipulating the very fabric of space-time, initiating new Big Bangs to seed fresh realities. If successful, humanity would transition from being inhabitants of the cosmos to its creators, ensuring that life endures even as the current universe fades into darkness. This vision is not merely a fantasy. It represents the logical extension of humanity's drive to explore, innovate, and survive. By embracing this vision, we affirm our commitment to life's resilience and its capacity for boundless growth. The universe may be vast and indifferent, but within it, humanity has the potential to create meaning and leave a legacy that resonates for eternity. Our story is just beginning. As we step into the cosmos, let us carry forward the values that define us: curiosity, creativity, and a deep respect for the interconnectedness of all things. In doing so, we ensure that our legacy is one of inspiration and hope, not exploitation or destruction. The infinite horizon is not just a challenge, it is a promise, a reminder that within the vastness of existence, there is always more to discover, create, and celebrate. The Cosmic Renaissance, humanity's expansion beyond time and space. As humanity sets its sights on the boundless expanse of the cosmos, the pursuit of exploration transforms into something far greater: a renaissance of existence itself. To inhabit the universe is not merely to travel its stars and planets, it is to fundamentally reimagine what it means to live, to create, and to persist. This is not just a journey of survival, but one of flourishing across dimensions, timelines, and possibilities, transcending the boundaries of time, space, and even identity. The first step in humanity's cosmic renaissance begins with securing a multi-planetary presence. Mars and the Moon serve as vital starting points, but they are far from the final destination. The Moon, with its proximity to Earth, offers a testing ground for long-term habitation and resource extraction. Using lunar regolith to construct habitats, harvesting water ice from its poles for life support and fuel, and building solar farms on its surface will lay the foundation for sustaining life in space. These efforts will teach us how to thrive in environments without an atmosphere or biosphere, preparing humanity for even more challenging frontiers. Mars, on the other hand, represents a more ambitious leap. Its surface, though barren and hostile, contains the elements necessary for supporting life: water ice, carbon dioxide, and abundant silicon for building materials. Early Martian colonies will rely on innovations like modular habitats that can be expanded as the population grows, nuclear-powered generators to provide consistent energy, and vertical farming systems to produce food. As these technologies mature, Mars will transition from an outpost of survival to a self-sustaining civilization. Terraforming Mars is an essential component of humanity's vision for the Red Planet. This colossal endeavor will involve warming its surface to release carbon dioxide trapped in its soil and polar caps, thickening the atmosphere to shield against radiation and enable liquid water to exist on the surface. Over centuries, this process could create conditions where humans could walk outdoors without protective suits, where rivers flow, and where Earth-like ecosystems flourish. Terraforming is not just a technical challenge, it is a declaration of humanity's intent to transform the cosmos into a place that supports life. While Mars and the Moon are immediate priorities, the icy moons of the outer planets beckon with the promise of discovery. Europa, with its subsurface ocean, may harbor the first evidence of extraterrestrial life within our solar system. Robotic submarines equipped with advanced sensors could penetrate its icy crust, exploring an alien ocean untouched by sunlight. Similarly, Titan, with its thick atmosphere and methane lakes, offers an environment rich in organic chemistry, a natural laboratory for understanding life's origins. The asteroid belt, often overlooked, is a treasure trove of resources that will fuel humanity's expansion. Composed of billions of rocky bodies, the belt contains vast quantities of metals like iron, nickel, and platinum, as well as water ice that can be converted into oxygen and hydrogen for life support and propulsion. Mining these asteroids will not only provide the raw materials for constructing habitats and spacecraft, but will also reduce humanity's reliance on Earth's finite resources. Automated mining drones, paired with orbital processing stations, will create an interplanetary supply chain, supporting both near-Earth industries and far-reaching missions. As humanity's presence expands within the solar system, the question of interstellar travel becomes increasingly urgent. To ensure the survival and growth of civilization, we must look beyond our solar neighborhood to the stars themselves. Interstellar travel, while daunting, is not beyond the realm of possibility. Current propulsion technologies, such as chemical rockets, are insufficient for such journeys, but new advancements hold promise. Nuclear fusion propulsion, for instance, could enable spacecraft to achieve speeds far greater than any current technology. By harnessing the energy released from fusing hydrogen isotopes, fusion engines could provide continuous thrust for years, reducing travel times to nearby stars to mere decades. Antimatter propulsion, though still theoretical, offers even greater potential. The annihilation of matter and antimatter releases energy with unparalleled efficiency, potentially enabling spacecraft to travel at a significant fraction of the speed of light. For journeys spanning centuries, generation ships offer a practical solution. These massive, self-contained vessels would function as independent ecosystems, supporting multiple generations of humans as they traverse the void. Aboard these ships, societies would evolve, developing new cultures, languages, and traditions. The challenge of designing such ships lies not only in creating sustainable life support systems, but also in ensuring social stability and psychological well-being over extended periods. Upon reaching distant star systems, humanity's first task will be to identify worlds suitable for colonization. Exoplanets in the habitable zones of their stars are prime candidates, offering the potential for liquid water and stable climates. However, even the most Earth-like planets will differ significantly from our home. Their atmospheres may be unbreathable, their gravitational forces unfamiliar, and their ecosystems completely alien. Terraforming will again play a central role. On planets with thin atmospheres, we may deploy atmospheric processors to release oxygen and nitrogen. On colder worlds, orbital mirrors could reflect sunlight, warming the surface and melting frozen water reserves. Genetic engineering could also play a pivotal role, creating crops and organisms adapted to the unique conditions of these new environments. As humanity spreads across the stars, we will inevitably encounter the question of extraterrestrial life. Microbial life, if discovered, will offer profound insights into the universality of biology and the conditions necessary for life to emerge. Intelligent life, on the other hand, poses both an opportunity and a challenge. Communication with extraterrestrial civilizations may require entirely new languages or modes of thought, and the ethical implications of such contact will be immense. The discovery of intelligent extraterrestrial civilizations would redefine humanity's place in the cosmos. We would no longer be alone but part of a broader community of sentient beings. This realization would challenge our philosophical and theological assumptions, forcing us to reconsider our values and priorities. How we choose to engage with such civilizations, whether as collaborators, competitors, or observers, will shape our legacy in the universe. Beyond the stars lies the multiverse, a concept that challenges our understanding of reality itself. If parallel universes exist, each governed by its own physical laws and histories, they represent an infinite frontier for exploration. Accessing these universes, should it prove possible, would require technologies that manipulate the fabric of space-time on an unprecedented scale. The discoveries awaiting us in the multiverse could provide answers to questions about the origins of existence, the nature of consciousness, and the fundamental principles that govern all reality. As we explore these new frontiers, humanity must prepare for the distant future of the universe. The cosmos, though vast and dynamic, is finite in its current form. Stars will burn out, galaxies will drift apart, and the universe will cool as entropy increases. To survive beyond this era, humanity must master the manipulation of energy and matter on an unimaginable scale. One possibility is harnessing the energy of black holes. By extracting energy from their accretion disks or using advanced technologies like the Penrose process, we could sustain civilizations even as the stars fade. Another possibility is the creation of artificial universes, engineered realms where life can continue indefinitely. Such acts would position humanity not just as participants in the cosmos, but as its creators, ensuring that life persists even as the current universe reaches its end. The journey toward cosmic immortality is not just a technological challenge, it is a philosophical and moral one. It forces us to confront questions about the nature of life, the meaning of existence, and the responsibilities of a species capable of reshaping the cosmos. As we transcend the boundaries of Earth and biology, what will remain of our humanity? How do we ensure that our actions reflect not just survival but the values that define us: curiosity, compassion, and creativity? In the face of an indifferent universe, humanity has the opportunity to create meaning. Each step into the cosmos, whether it is establishing a colony on Mars, sending a message to another galaxy, or exploring the multiverse, is an affirmation of life's resilience and its capacity to dream. The stars do not need us, but we need them. They are the canvas on which we paint our legacy, the infinite horizon that calls us to become more than we are. When the last stars fade and the universe grows cold, humanity's story may still continue. Whether as biological beings, digital consciousness, or creators of new realities, we will have proven that life is not bound by its origins. It is a force of endless potential, capable of reaching across the void and leaving a mark that resonates for eternity. This is the symphony of existence, a melody composed not just of survival, but of growth, discovery, and the unyielding belief that the cosmos is not just a place we inhabit, but a destiny we shape. The Symphony of Creation, humanity's path to cosmic stewardship. As humanity charts its course into the boundless reaches of the cosmos, the notion of survival transforms into something far more profound: stewardship. The universe, vast and indifferent, is also teeming with potential worlds waiting to be nurtured, mysteries waiting to be unraveled, and perhaps life waiting to be discovered or created. Our role within this grand expanse is not merely to exist but to guide, protect, and cultivate, ensuring that the essence of life flourishes in forms and dimensions yet unimagined. This cosmic stewardship begins with the foundational task of building resilient civilizations beyond Earth. Mars, the Moon, and orbital habitats are stepping stones, not endpoints. Each success in establishing these footholds represents a deeper understanding of how to engineer sustainable ecosystems. Closed-loop life support systems, capable of recycling air, water, and nutrients indefinitely, will be the cornerstone of these efforts. Advances in artificial photosynthesis, bioengineered crops, and water reclamation technologies will enable human communities to thrive even in the harshest environments. As these technologies mature, humanity will expand its reach to the outer solar system. The moons of Jupiter and Saturn, Europa, Ganymede, Titan, and Enceladus, are particularly promising targets. Europa's subsurface ocean, shielded by a thick crust of ice, is a prime candidate for life. Robotic explorers and eventual human missions could reveal whether this alien sea harbors microbial ecosystems or even more complex organisms. Titan's methane lakes and dense atmosphere, though inhospitable to human life as we know it, provide a unique laboratory for studying prebiotic chemistry and the potential for alternative forms of life. Establishing permanent outposts on these moons will require innovative approaches to energy and materials science. Nuclear power, supplemented by localized solar and geothermal energy, will drive these settlements. Structures will need to be built from local resources, such as water, ice, and silicate minerals, to minimize reliance on Earth. Over time, these outposts could evolve into thriving colonies, interconnected by transport networks and communication relays, forming a vibrant human presence in the outer solar system. The next leap, interstellar travel, ushers humanity into an entirely new era. The distances between stars are almost incomprehensible. Even Proxima Centauri, the closest star to our Sun, lies over 4 light-years away. To bridge these gaps, humanity must develop propulsion systems capable of achieving relativistic speeds. Concepts like nuclear fusion engines and antimatter propulsion are within the realm of theoretical physics, but their practical implementation will require unprecedented advancements in energy generation, fuel production, and spacecraft design. One of the most ambitious ideas for interstellar travel is the concept of light sails powered by lasers. Initiatives like Breakthrough Starshot propose deploying tiny spacecraft equipped with reflective sails that harness powerful laser beams from Earth or orbital stations. These crafts could reach speeds of up to 20% the speed of light, allowing them to travel to nearby stars within decades. While such missions would initially be limited to robotic probes, they represent a crucial step toward human interstellar exploration. Generation ships, self-contained, city-sized vessels designed for multi-generational voyages, offer another solution for interstellar colonization. These ships would carry entire communities, complete with their own cultures, economies, and educational systems. Advanced artificial intelligence would oversee ship operations, ensuring stability and sustainability over centuries-long journeys. Within these floating worlds, humanity would adapt and evolve, preserving its heritage while forging new identities. Upon arriving at distant star systems, humanity will encounter planets with conditions vastly different from Earth's. Some may have atmospheres thick with methane, oceans of ammonia, or gravity far greater than what humans are accustomed to. Adapting to these environments will require a combination of terraforming and biological innovation. Terraforming efforts might involve deploying fleets of atmospheric processors to adjust gas compositions, constructing solar reflectors to regulate temperature, or introducing hardy, genetically engineered organisms to reshape planetary ecosystems. Where terraforming is impractical, humanity itself must adapt. Advances in genetic engineering could enable humans to survive in environments previously deemed uninhabitable. Enhanced resistance to radiation, the ability to process alien nutrients, and even modifications to respiratory systems to utilize non-oxygen atmospheres are within the realm of possibility. Over millennia, these adaptations could lead to the emergence of distinct human subspecies, each uniquely suited to its planetary home. Beyond the challenges of adaptation lies the tantalizing possibility of encountering extraterrestrial intelligence. The discovery of microbial life within our solar system or evidence of advanced civilizations elsewhere in the galaxy would fundamentally alter humanity's understanding of its place in the cosmos. Such encounters would present profound ethical and philosophical dilemmas. How should we approach beings who may view reality in ways entirely foreign to us? What rights and responsibilities do we owe to other forms of life, especially those capable of sentience and self-awareness? Communication with extraterrestrial civilizations might require entirely new technologies and methods of understanding. Advanced AI systems capable of deciphering alien languages or translating across radically different modes of cognition could bridge the gap. These interactions, if handled with respect and humility, could lead to a sharing of knowledge that benefits both parties, enriching our understanding of science, philosophy, and the nature of existence itself. The exploration of the multiverse, should it prove accessible, extends these challenges and opportunities to an infinite scale. Parallel universes, governed by different physical laws or histories, represent the ultimate frontier. Each universe could contain unique forms of life, matter, and energy, offering insights into the nature of existence that defy comprehension. Accessing these realms would require mastery over space-time, enabling humanity to traverse dimensions or create portals between realities. As humanity expands its influence, it must also prepare for the far future of the universe itself. Stars will eventually burn out, galaxies will drift apart, and the cosmos will cool as entropy increases. In this distant era, survival will depend on humanity's ability to manipulate energy and matter on an unprecedented scale. Dyson spheres, built around dying stars, could extract their remaining energy. Black holes, with their immense gravitational power, could be harnessed as energy sources using advanced technologies like Hawking radiation collectors. In the ultimate scenario, humanity may transcend the universe altogether, creating artificial realities or even new universes. By manipulating the fundamental forces of nature, advanced civilizations could initiate new Big Bangs, seeding fresh realms of existence. These acts would elevate humanity to the role of cosmic creators, ensuring that life persists even as the current universe fades into darkness. Throughout this journey, humanity's identity will inevitably evolve. As we transcend the boundaries of biology, geography, and even physics, what it means to be human will shift. Digital consciousness, artificial life forms, and genetically engineered descendants may coexist alongside unmodified humans, each contributing to the collective legacy of our species. This diversity will not weaken humanity but strengthen it, showcasing the adaptability and creativity that define us. The ultimate measure of humanity's success will not be the number of planets colonized or the distance traveled, but the values upheld along the way. Curiosity, compassion, and a commitment to preserving life in all its forms must guide every decision. In a universe that offers no inherent meaning, humanity has the opportunity to create its own, shaping a legacy that resonates across time and space. When the last stars fade and the universe grows cold, humanity's story may still continue. Whether as biological beings, digital consciousness, or creators of new realities, we will have proven that life is not bound by its origins. It is a force of endless potential, capable of reaching across the void and leaving a mark that echoes for eternity. The symphony of creation, woven with the threads of exploration, growth, and resilience, will serve as a testament to the boundless spirit of humanity. The cosmos is not merely a backdrop for our existence, it is a canvas, a stage, and an endless horizon. Each step we take into its depths affirms the power of life to overcome, to adapt, and to dream. The universe awaits, and in its vastness, we will find not just survival but a destiny worthy of our highest aspirations. This is humanity's cosmic renaissance, a journey not just to the stars but to the infinite possibilities of what we can become. The infinite legacy, humanity's universal transformation. To envision humanity's ultimate role within the cosmos is to contemplate a transformation so profound that it transcends the confines of biology, culture, and even the physical universe. Our legacy, if it is to endure, must reflect not only our ability to adapt and innovate, but also our capacity to infuse meaning into the vast, indifferent expanse of the cosmos. This legacy will be a testament to life's resilience, creativity, and unyielding drive to persist and thrive. The first chapters of this legacy are already being written on Earth and in the nearby reaches of our solar system. The Moon serves as our immediate proving ground, offering a platform for testing technologies and methodologies critical to sustainable living beyond Earth. Lunar bases, built using local resources like regolith and powered by solar energy, will demonstrate our ability to thrive in airless, hostile environments. These early outposts will pave the way for more ambitious settlements on Mars, where challenges like thin atmospheres, extreme temperatures, and high radiation levels will test the limits of human ingenuity. Terraforming Mars is a long-term vision that underscores humanity's ambition. The process would involve warming the planet to release carbon dioxide, thickening its atmosphere to create a greenhouse effect, and introducing oxygen-generating organisms to support life. Such an endeavor, spanning centuries, represents humanity's first attempt to actively transform a planet, turning a barren world into a cradle for ecosystems. While the technical challenges are immense, the act of terraforming would symbolize humanity's ability to shape the cosmos to foster life. The asteroid belt offers a wealth of resources that will fuel humanity's expansion. These rocky bodies contain vast quantities of metals like nickel, cobalt, and platinum, as well as water ice, which can be converted into hydrogen and oxygen for fuel and life support. Mining asteroids will reduce our dependence on Earth's finite resources, enabling the construction of spacecraft, habitats, and other infrastructure needed for interplanetary and eventually interstellar exploration. Robotic mining fleets, equipped with advanced AI, will make this vision a reality, establishing a network of resource hubs throughout the solar system. Jupiter's and Saturn's moons present the next frontier. Europa, with its subsurface ocean, is a prime candidate for life within our solar system. Robotic probes equipped with advanced drilling and exploration tools could penetrate its icy crust, exploring an alien ocean teeming with possibilities. Titan, with its thick atmosphere and methane lakes, offers an entirely different environment, one rich in organic molecules that could reveal new pathways for life. Colonizing these moons will require habitats capable of withstanding extreme conditions, powered by nuclear and geothermal energy sources. Beyond the solar system lies the dream of interstellar travel. The distances involved are staggering, with even the nearest stars requiring journeys of decades or centuries at attainable speeds. Propulsion technologies such as nuclear fusion engines and antimatter drives offer plausible paths forward. Fusion engines, powered by the same reactions that fuel stars, could provide continuous thrust for extended missions, while antimatter drives, harnessing the annihilation of matter and antimatter, promise unparalleled energy efficiency. More speculative concepts, like the Alcubierre warp drive, challenge the boundaries of physics. By bending space-time itself, a warp drive could theoretically allow faster-than-light travel, bypassing the limitations imposed by relativity. Such technology would require the discovery or creation of exotic matter with negative energy density, a challenge that lies at the cutting edge of theoretical physics. While these ideas remain speculative, they exemplify humanity's ability to dream beyond its current constraints. Generation ships offer a more practical solution for interstellar colonization. These massive, self-sustaining vessels would function as miniature worlds, supporting human populations for centuries-long voyages. Equipped with advanced life support systems, artificial gravity, and renewable energy sources, generation ships would carry not only people but also the seeds of Earth's ecosystems, ensuring that humanity's biological and cultural heritage survives and evolves. Over time, these ships would become their own societies, shaped by the unique challenges and opportunities of life in transit. Upon arriving at distant star systems, humanity will face the challenge of colonizing alien worlds. Exoplanets in the habitable zones of their stars offer the most promising targets, but even these will require significant adaptation. Terraforming efforts might involve releasing greenhouse gases to warm the surface, constructing orbital reflectors to increase sunlight, or deploying genetically engineered organisms to modify the atmosphere. Each planet will present unique challenges, requiring tailored solutions that blend technology, biology, and environmental science. For worlds where terraforming is impractical, humanity must adapt to the environment rather than altering it. Genetic engineering could allow humans to survive in high radiation environments, metabolize alien nutrients, or withstand extreme temperatures. Over generations, these adaptations could lead to the emergence of new human subspecies, each uniquely suited to its planetary home. This diversification, far from fracturing humanity, would enrich it, showcasing our capacity for resilience and creativity. As humanity spreads across the stars, the discovery of extraterrestrial life becomes increasingly likely. Microbial life, if found, would revolutionize our understanding of biology and the conditions necessary for life to emerge. Intelligent civilizations, should we encounter them, would pose even greater challenges and opportunities. How we choose to interact with such beings, whether as partners, observers, or competitors, will define our legacy as a species. The multiverse, if accessible, extends humanity's horizons even further. Parallel universes, each with its own physical laws and histories, represent an infinite frontier for exploration. The ability to traverse, or even create universes, would elevate humanity from inhabitants of the cosmos to architects of existence. What might we learn from universes where time flows backward, where life evolves in forms we cannot imagine, or where entirely new dimensions of reality exist? These discoveries would challenge and expand our understanding of existence itself. As the universe ages, humanity must prepare for its ultimate destiny. Stars will burn out, galaxies will drift apart, and the cosmos will cool as entropy increases. In this distant future, survival will depend on mastering energy sources beyond anything currently conceivable. Black holes, with their immense gravitational energy, could be harnessed through technologies like Hawking radiation collectors. Artificial stars, powered by controlled fusion reactions, could sustain life in a darkened universe. In the ultimate scenario, humanity might create new universes, engineered realms, where life can continue indefinitely. By manipulating the fundamental forces of nature, advanced civilizations could initiate new Big Bangs, seeding fresh realities. These acts would position humanity not just as participants in the cosmos, but as its creators, ensuring that life persists even as the current universe fades into darkness. Throughout this journey, humanity's identity will inevitably evolve. As we transcend the boundaries of biology, geography, and even physics, what it means to be human will shift. Digital consciousness, artificial lifeforms, and genetically engineered descendants will coexist alongside unmodified humans, each contributing to the collective legacy of our species. This diversity will not weaken humanity but strengthen it, reflecting the adaptability and creativity that define us. Ultimately, humanity's legacy will be measured not by the number of planets colonized or the distance traveled, but by the values upheld along the way. Curiosity, compassion, and a commitment to preserving life in all its forms must guide every decision. In a universe that offers no inherent meaning, humanity has the opportunity to create its own, shaping a legacy that resonates across time and space. When the last stars fade and the universe grows cold, humanity's story may still continue. Whether as biological beings, digital consciousness, or creators of new realities, we will have proven that life is not bound by its origins. It is a force of endless potential, capable of reaching across the void and leaving a mark that echoes for eternity. The infinite horizon is not just a challenge, it is a promise, a reminder that within the vastness of existence, there is always more to discover, create, and celebrate. This is the essence of humanity's infinite legacy, a story without end, a testament to the boundless spirit of life.